So, going to go through, talk about factor analysis stuff today. Again, thanks for coming in. I think this is a helpful and a sort of informative material to work through, just because EFA stuff is going to come up a lot, regardless of what area of research that you're working in. Most of the time, in terms of psychometric studies, is the measure that we've got measuring what it's supposed to? Is it doing the things and behaving the way that it should? EFA is one of our primary tools for going through and looking at structural properties of measures and starting to infer some stuff there. We're going to jump through some of this stuff pretty quick because we only have sort of the time of day to move through. But thinking about what we want to be doing, so what the goals of our factor analytic procedures are. One, summarizing patterns of association among a set of observed variables, right? We have 10 different variables most often when we're working this. These are indicators on some measure, right? What we want to do is make some determination or have some explanation for why are these items related to one another, right? What's accounting for the interrelation among these items, right? We also can use this to test hypotheses involving the structure and unobserved construction processes that are giving rise to those unobserved scores. So in essence, I have a measure of extroversion, right? But extroversion is a hypothetical construct. I've got some indicators that I think should tap into extroversion and some other items that should tap into neuroticism. But those items and those scores aren't literally the construct that we're measuring. Those are sort of fallible indicators of this unobserved construct. But if these are the items that should tap into extroversion and these are the items that should tap into neuroticism, then we should start to see certain things come up within these analyses if our theoretical assumptions are correct. We can start to provide operational definitions for these unobserved constructs based on general linear models, equation stuff. This is essentially what we're doing anytime we create a sum score on a measure, right? I can't grab Trent's extroversion like that because that's not a real thing, right? But what I can do is I can operationalize extroversion as scores on this measure as evidenced through, if we want to get really specific, some linear combination indicating the relation of this unobserved construct to these specific indicators. And in some areas, what we'll see is using factor analyses to start to reduce large numbers, large set of collinear indicators down into something that's a more manageable set of component constructs. Now, we're going to talk about some problems with this, and this is often not something we use factor analysis for in our literature, but it's something that you can do with this. So again, our analyses, we're going to go through, establish a set of linear weights. We're going to call these factors, and these weights or factors are going to summarize the relationships between our variables, and what we're doing in essence here is trying to replicate the associations that we see in the observed data. With any type of factor analytic procedure, structural equation modeling type of stuff, in essence, this is what we're doing. We're going through and saying, okay, here are the observed relationships. Here's the covariance or the correlation matrix. What we want to do is come up with some linear model that perfectly replicates sort of this thing that we've actually observed. And the extent to which we can replicate that with our assigned weights is in some ways determination of adequacy of our model. Sometimes we do a very good job, sometimes not so good. We'll go through and take a look at how we determine some of that. So, move this. Our exploratory factor measures, we see these a lot. People do this all the time. But again, it's one of these things, oftentimes it's people running with scissors, right? Like, you should know what you're doing before you go through and do it. If you don't know, if you're just pointing and clicking, don't understand what these analyses do, how to interpret them, how to execute them properly, we get a lot of trash factor analyses out there in the universe if people aren't regulating this. If you run a regression model, the regression model is the regression model, and that's what you get, right? Depending on how you execute these factor analytic techniques, you can get sometimes very, very different solutions, and sometimes those solutions may or may not make sense, right? You can't just stuff something in there and say, oh, well, I did it. and this is the way that you do it, have to be thinking about what's going on, how these items are related to one another, and sort of how we go through and start extracting stuff. So hopefully you'll get just a quick overview on that stuff today. So research questions, number one, how many reliable conceptually meaning factors do I need to summarize associations between sort of my observed scores? Okay, this is important. How many do I need? The idea, this starts to get at parsimony, right? Because if I have a 10-item measure and I extract 10 factors, then I'll perfectly reproduce my correlation matrix, and then I'm good, right? So why might I not be happy with that solution?
Because you would like to explain fewer factors than one for every.
Yeah, that's ridiculous, right? Like, then I don't need to run analysis. I'm just saying, oh, each one of these items represents a different factor with correlation 1 with its corresponding factor, right? But you'll start to see within these analyses, the more factors that you extract, the greater proportion of variability in your outcome that you're accounting for. And so what sometimes happens is people are like, oh, well, I just keep extracting factors and it makes my solution better, right? At some point you have to say, all right, conceptually, what's the minimum number of factors that I can go through and reasonably account for why these variables are correlated with one another. Also wanting to look at underlying processes, constructs, driving relations. You'll see these ever started to break into EFA types of research, or generally confirmatory factor models, things along those lines. You'll often see, and seems kind of weird, we've got our factors, right? These are our unobserved factors, and then we have arrows pointing from the unobserved factor to our individual indicators, right? Which seems sometimes like we should have, because we're estimating these based on our indicators, that the arrows should be pointing the opposite direction. Why don't, Sean, any idea why these arrows are sort of going the opposite way of what we might expect?
Just because the questions are scale items and complex different parts of the
Right, right. So the idea is, from a theoretical standpoint, that we have these unobserved constructs or processes that are causing these items to differ and sort of vary, right? Sort of your level of extroversion, Sean, is going to produce a different score on this measure than Trent's level of extroversion. So we're going to see differences in your score versus his score based on this latent unobserved construct of extroversion, not the other way around, right? Your score that you write down doesn't drive your extroversion, it's your extroversion that's driving the score. And with these, what we're wanting to do is go through and start to look, oftentimes as we start to get into more complex confirmatory models, sort of the structure of our hypothetical construction, whether or not our assessment measures are accurately tapping into that. We can ask to what degree our factors account for variability in our observed data. If we got a good measure, our factor structure should account for a good proportion of variability in our outcome, right? If it doesn't, if I say, oh, I've got a 5-factor structure that accounts for 20% of the variability of my scores, I'm not super excited about that, right? Because that suggests that 80% of the differences of the variability in scores that I'm seeing are not accounted for by sort of this model that should tell me that this is why we're having the scores that we're having, right? So I want to go through and take a look at that. We can also start to make some estimates, numerical estimates of these individual factors and say, what is Sarah's latent extroversion score, right? We can't see it, but based on the data that we have in our solution, can we go through and start to attach scores to your extroversion? So not sums of our individual items. Can we actually estimate sort of your unobserved score here? We've got some techniques, but there are some problems with that we'll go through and talk about, okay? Questions about purpose, what we're doing with these, why we would do these, sort of different uses of factor analyses that maybe you've come across that we haven't touched on in sort of this brief overview? Cool, all right. Overview some basic procedures. If we're going through, and so we're doing rudimentary, or not rudimentary, it's complicated, but sort of just very sort of initial, straightforward we're getting started and sort of wanting to do an initial analysis of sort of the underlying structure of some scores. One of the first things we need to do once we've gone through, we've got a new measure, right? And so we've generated a bunch of items that we believe should tap into this sort of this construct of constructs that we're interested in looking at. We've got our data, as we say, all right, what do we want to do? We're going to run an EFA. Which one of the first things we need to do is determine how many factors are we going to extract, okay? Now, exploratory factor analysis, so the idea is that we're walking into this without any assumptions of sort of the number. I mean, we might have some ideas, right? We probably just didn't sort of brainstorm a bunch of random items and put it together because we thought something might come out. We probably have ideas about how many factors will come out of these data. But if you're doing this type of stuff, if you're doing measure development, be prepared to be incredibly disappointed. Like, no matter how well you go through and generate items and things like that, they never turn out the way that you're supposed to. Like, you're like, oh, this is an awesome item and it's going to map onto this perfectly, and it's a crap item and it never turns out no matter how you want to have it in there. Now, that's not to say you should throw it out necessarily. There's some things to go through and think about, but this is messy, 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 particularly if you're developing things. And so when you go through, you may say, oh, I've sort of generated a measure. I've got these 2 scales. You may end up with 3 or 4 or 1. Or again, a crap solution that doesn't tell you much of anything, right? And so first thing that we need to do is determine how many unobserved factors are we going to go through and extract, okay? Essentially what this involves is, based on the data, trying to make a determination of the number of linear combinations that we're going to need in order to adequately summarize our observed correlations. So within these extraction procedures, each linear combination or factor is going to account for some unique proportion of variability in the data. The extraction procedure that we're going to use is going to determine on whether or not we're interested in parceling out all available variability in the data, or only shared variability among our items. This is going to start to become important from a theoretical standpoint. And so characteristics of the data, type and number of available linear are going to impact the number of available linear combinations that we can go through. Several techniques for extraction. We're going to go through a couple different types. Huge literature on these procedures. There's big, thick books. We're just going to go through the very, very basics. But the nice thing is that unless you've got weird data or some specific considerations, these should cover 90% of your needs most of the time. There are esoteric types of things that you may need for very, very specific situations. But again, if you've got a good, strong structure and a good, strong measure, the extraction procedures you're using shouldn't impact things all that much, okay? So extraction, determining how many factors are we going to pull out, sort of what will these data support in terms of reasonable, unique factors. Rotation, once we've gone through and extracted those factors, what we then need to do is go through and say, can we sort of mathematically reconfigure this variance or covariance to start to make our linear combinations more interpretable, okay? If we think about, and we'll get into this in a little bit, we go through and we say, all right, there are 3 components. There are 3, I can specify 3 linear combinations, basically 3 unique regressions that go through, or functions that go through and capture, say, 60% of the variability in this. After that was sort of not much going on. But then what we need to do is go through and start to make some sense of this, right? You can't just say, oh, this measure has 3 factors and leave it at that, right? You have to just tell people what that factor is. Now, tricky thing with factor analyses is there are an infinite number of ways to interpret those extracted factors. Depending on how we go through and mathematically rotate, we'll get a unique solution for every single rotation that we have, right? And so what we want to do with our rotation is start to optimize sort of the patterning of these functions in sort of multivariate space in order to sort of get everything kind of clustered and separated to the greatest extent possible. Think about the rotation procedures that we choose are based primarily on whether or not we want our unobserved factors to correlate or not. But our rotation procedure doesn't change the proportion of variability that we pull out from. This is kind of difficult to wrap our head around. We'll go through and get into this a little bit more. But the idea is, think about this in terms, think about rotation is the same thing with, we've talked about sums of squares, right? And variance and standard deviation. How are sums of squares, variance, and standard deviation related to one another? Gina?
Sums of squares, that's your variance. Variance is lower down is your standard deviation.
Okay. So what are all three of those metrics? What are they indicators of?
Is it how you pool the variance?
Okay, so kind of how you pool, and so the calculation's a little bit different, right? But at the end of the day, they're all metrics of variability, right? It's just they're telling you the same thing. They're just different. It's the same thing. It's just in different languages, right? Sums of squares, probably not terribly useful in terms of, oh, I sort of look at a sums of squares and I say, oh, that's a big sums of squares. Same thing with variance, right? Hard to put an interpretation on that. But if we take that, sort of run it through some stuff, and then we have a standard deviation, we can say, oh, well, that's a standard deviation. That's going to be sort of on average within the set, the distance of any two randomly selected scores from there, right? And so with rotation is going to be the same thing. It doesn't change our solution. It just helps us facilitate interpretation of sort of the factors that we've extracted here. So, so we've gone through, we've chosen a rotation strategy. Then we have to go through and provide some sort of interpretation of what these factors represent, okay? We can go through and some things we'll want to be taking a look at here. The proportion of variability, covariability attributable to the model, right? How much variability in our data does this solution account for? Proportion of variability, covariability attributable to a factor. So this individual factor, how much variability in these data can I assign to this specific factor? Proportion of variability in each indicator or item accounted for by the model, right? This is going to be a commonality, right? If my model is good and my solution is doing a good job accounting for variability in item 1, I should see a high proportion of variability in item 1 being accounted for by my solution, right? If my solution doesn't account for a good deal of variability in item 1, either my solution's no good or maybe item 1 is no good. These are the things we have to go through and think about. Correlation between variables and unobserved factors. These are going to be our factor loadings. How close or how tightly how good are our individual items, how good are they as indicators of the underlying factor? If we've got high factor loadings, that's suggesting that this item that I've written does a very nice job of mapping on, at least within the context of these data, capturing sort of the underlying construct. Or if that factor loading is really weak, it suggests that it's not a very good item, right? And then correlations between our unobserved factors, depending on the rotation that we select. Sometimes we can go through and start to say, all right, my measure captures three unobserved factors, but I'm expecting these unobserved factors to have some relation with one another. They're not going to be correlated 0, which makes some sense if it's all part of the same measure, right? Like, here's my measure of 3 uncorrelated things. It's not typically what we run into, right? But so wanting to go through and say, all right, sort of in the purest sense, what's the relation between these unobserved factors, something that we can get with an EFA, okay? So one thing to know and sort of be aware of is you're going through doing your own research, evaluating other research. Best practice methods for EFA almost always going to involve interpretation, estimation, multiple solutions, right? This is not an exact science by any stretch of the imagination. It's lots of subjective stuff goes in and sort of your own interpretation of data, right? And so you want to be able to go through and justify and sort of know why you've selected and be able to defend the solution that you've decided upon, okay? And so almost always this is going to involve going through and saying, all right, well, let's see within these data, in best case scenario, 2 of those will be awful and 1 of those will make a lot of sense, and it gives you a nice clean idea of how to move forward, but sometimes it won't. Sometimes judgment is going to come into this, and so what you want to do is know know what you're doing, how to reasonably interpret the things that you're doing, know the strengths and limitations of different choices moving forward, and sort of this complexity and the subjectivity of this analysis is a large reason why this ends up being misused by people who should probably read a little bit more before they decide to jump in the data and start extracting factors, right? And that's not to say that people are sort of not, no, it is saying that they're not doing good stuff, but it's just one of these things. You want to be educated on your techniques before you jump in and start using these, particularly with this stuff. This isn't a plug and play type of analysis, right? As you'll see if you go through and take a look at that 60-page PDF of measure that we were playing around with. I mean, it's just pages upon pages and printing things out and sort of looking at loadings and like, well, that's not good. What do we need to go through? Let's cut these items and rerun this. It's an iterative process, and it can be quite time-consuming and when done correctly. So, thinking about extraction. Questions up to this point? Okay. If we're talking about exploratory factor analyses, EFA is kind of a broad catch-all term for a number of different procedures, some of which aren't necessarily factor analyses proper. And a lot of this is based on the methods that we're going through and using to extract data. Methods that we can go through and procedures that we can go through to start to extract or explore the number of factors to extract. Principal components, principal factors, these are the 2 that we're going to work with today. But there are other types of things that we can use, maximum likelihood, unweighted least squares, generalized least squares, image alpha factoring. All these different extraction procedures do slightly different things. Think about this in terms of our regression models. We sort of fell back on ordinary least squares, right? That was our technique or procedure that we use to estimate our regression models, but there are others out there. Same thing with our extraction methods. People have developed a lot of these. Some of these have some considerable strengths. Some of them are sort of developed to identify or to address a very, very narrow set of circumstances, right? In general, as you're going through and running these, again, principal factors, principal components are going to be your primary extraction techniques. You're probably going to want to have a good reason if you start to deviate into something else aside from just to be special and unique and do something that you didn't need to do when principal components, principal factors will be perfectly fine. All of these extraction techniques are going to extract and calculate orthogonal factors or components, again, intended to reproduce observed correlation matrix R, right? Each one of these is using slightly different procedures, going through, and so the idea being we're going to extract a number of uncorrelated components to go through and do our best job of recreating this correlation matrix. As I said before, just being a little bit different in how they're going through and starting to pull this stuff around. But as I mentioned previously, again, the extraction procedure that you're using, if you've got a large sample, if you've got a good number of variables, if all of these have similar and strong commonality estimates, you shouldn't get wildly different solutions depending on what extraction technique that you use, okay? Basically, if your data are good and you've got a good, reliable, and replicable solution in your data, you should be able to go through and use these fairly interchangeably and not get terribly different scores. If you start getting different solutions based on your extraction method, that's probably an indicator that you've got something wonky going on in your data. You need to go through and figure out why you're not getting consistency across these different extraction methods. Okay. So first thing we're going to talk about is principal components. Principal components technically isn't a factor analytic procedure. Principal components is data reduction procedure. what we're doing is we're pulling out linear components or linear combinations, most technically identified as components, not factors, okay? And so the reason behind this is within a principal components analysis, what we're doing is we're analyzing full correlation matrix. So in this example, we've got a set of 4 scores, right? So this is correlation of our matrix of our 4 scores. We've got correlations between individual items here in the off diagonal. In the diagonal, we have units of 1 along this, indicating 1 unit of variance, right? We go through and standardize, sort of basically your correlation matrix is a standardized variance covariance matrix. Within this, we're just standardizing everything. So our unit of variance in the correlation matrix is 1. Okay, so we've got 1s along the diagonal, right? Indicating variability within all of our items. And so the aim of our PCA is going to go through and extract the maximum amount of variance within each one of our components, okay? So we've got our correlation matrix here. And what we're going to do is we're going to say, okay, SPSS, go ahead and engage principal components now. Run through. And what SPSS is going to do is it's going to go through and it's going to extract a first component that's going to be a linear combination, sort of some equation or some sort of general linear equation that's going to go through and it's going to maximize the amount of variance that you can extract across component scores or across component items. So what it's going to do, think of this conceptually as your first component in PCA is going to go through and it's going to say, all right, here's all the variance among these scores. How much of this variability can I get with if there's one regression equation, say? Okay, it's more complicated than that. But basically, so we're going to have this one component that goes through and gets everything that's shared among these items that I can pull out. Okay, yeah.
Is that kind of just R squared of a regression paper?
Kind of. I mean, similar. Not exactly, but that's not a bad way to start thinking about it, right? So basically what we're going to do is we're going to sweep up all the shared stuff with this first component that we can gather up among our items. So I've got 10 items on this measure. What's the best linear combination of weights for each one of these items that it will go through and capture a maximum amount of shared variability in these data, okay? And then what you're going to do is like, okay, we've got that. So there's my first component. What I'm going to do with the second component is go through and say, all right, with everything that's left over, what's a new unique set of weights that I can go through and scrap up all sort of as much variability as I can with this next component, okay? And so by definition, when we talk about these as uncorrelated components, by definition, this first component got all this stuff that was shared among the items, and then the second component is coming in with all the unique stuff. All the unique stuff has nothing to do with this one, right? And so now I've got a new combination of weights that are extracting, sort of vacuuming up all the rest of the shared stuff, right? And then we've got a third one that we can go on, and so after we do that, sort of move on, so on and so forth. And so we can continue to extract components with the number of components that are available for extraction equal to the number of variables in the analyses, right? So if I've got a 10-item measure, in theory, and if everything's going correctly, I should be able to extract a maximum of 10 components. And by the time I get to the 10th component, I've perfectly reproduced my correlation matrix here, okay? Now there's an asterisk on this. That asterisk you can get if my items are largely redundant or collinear. I've got singularity in there somewhere. You may start to get an error and may not be able to extract 10 components if items 5 and 8 are basically duplicates of one another. You have problems with your matrices and going through that. But in theory, the number of factors that you will be able to extract is going to equal the number of variables that you have in your analyses. Okay? So as we're going through, as you can imagine, what ends up happening, our components tend to be ordered. Our first component extracting the most variance, the last vacuuming up the very least, And again, final solution, perfectly reproducing our correlation matrix when all components are considered. Okay. So this is a lot of sort of abstract sort of matrix math types of stuff, but people get a general idea of what's going on with these components. Think about it this way. Let's say I've got 3 factors, right? And I've got a measure that has 3 factors. And I've created a perfect measure where each one of these factors is uncorrelated with the other one. And all items loading on this factor, after I account for that, are completely unrelated to any of the other items, right? And so what I do with my PCA is I go through and I say, all right, what's the maximum amount of shared variability that I can get among these items? Well, maybe it's factor 1, because factor 1 is neuroticism, and neuroticism is always the biggest factor, right? So I go through and sweep up all stuff that's neuroticism, and so I get factor loadings of 1 for all the items on my neuroticism scale and 0 on everything else, because everything else is unrelated once I get that, right? And so I go through, and this is the greatest amount of variability with a single linear combination that I can get out of that, and basically that all corresponds to neuroticism. So I sweep that up, and then I say, okay, what's left over? Well, my factor 2. Factor 2 is extroversion, right? And so I go through and I've created a beautiful scale where all the items are perfect indicators of extroversion, and I go through and I say, oh, hey, I can collect these items that are working together. That gets me my extroversion scale, and then a third one that's openness or sort of whatever else we want to go through and take a look at, right? And so with each factor that we go through now in that example, we would get 3 factors and then have no more variability to collect. But in general, because our measures are our indicators are never perfect indicators of our underlying constructs, we're going to have other stuff going on in there, right? So maybe my items capture some neuroticism, right? But then also some extra sort of mood-specific stuff that's going on right now. And so I'm going to get a lot of neuroticism with first factor, but I'm still going to have other stuff going on, right? And so this is where we're going through with these components. And again, in theory, we can extract our maximum number of components to be extracted is going to be equal to the number of variables in our set. All right, so if we're going through and thinking, and again, keep an eye on this, right? So with our principal components, what we're doing is we're going through and analyzing this correlation matrix R, where we have 1 unit of variability for each one of our items, right? Each item has a total variability of 1. And so what we're doing with our PCR, our principal components, we're going through and we're starting to go through and extract within each one of these components all observed variance within the correlation matrix, okay? And so if we're looking and talking about all variability in the correlation matrix, we're talking about different types of variance, right? We've got shared variance. This is the stuff that we want, right? This is the shared variance between sort of our items that should be all working together, right? So this is systematic variance that's shared with other variables in the model. But we're also going to scoop up here, we're also going to get unique variance, right? Our unique variance this is systematic variance that's unrelated to other variables in the model. Sort of scores on this item differ systematically across people for some reason, but not for any reason that's related to any of the other items. And that's going to be a unique variance. And then also error variance is going to get in there, right? That's just the random static that's going on that's attributable to measurement error, things going on around you at the time, just random stuff that goes on, okay? And so when we're looking at our principal components, our components are just an aggregate of our correlated variance. Again, what we're trying to do here is just we're trying to maximize the variance that we can extract using a parsimonious set of components, right? Here's my, I don't know, what's up? Well, so it's sausages, and so when I was putting this together, so I was thinking about it, I'm like, okay, what's a good analogy for PCA? So it's like sausage factory, right? Like you just like everything that goes in there, we're just grinding it all up. We don't care what it is or why it's in there. We're just sort of linking these up and sort of creating these components.
Excuse me as I vomit.
Well, made the mistake of Google imaging sausage factory. The first time I put
Oh,
that up
no.
was not give me images that I was looking for. So, hope that doesn't come up for tenure. We gone through and took a look at your search history. But the problem is, right, are we happy with just scooping up all variability in our data set, right? Because again, oftentimes from a psychological perspective, what we're trying to do is we're interested in refining down these pure underlying constructs, right? So what are the common constructs that are giving drive to associations among these individual variables, right? And so why might just be scooping up everything be problematic if our intent is to go through and extract and sort of try and identify sort of these unique theoretical components, these unobserved constructs that are giving rise to our observed scores on our items? Why might we not be happy with a PCA from a conceptual standpoint? Yeah, it's recording. Yeah.
Maybe there's like another factor that we weren't aware of, like we weren't thinking of, and we might miss out on that.
Okay, so.
Sweeping everything away.
Right, but again, with this iterative extraction, we're just going through and we're pulling stuff out and pulling stuff out and pulling stuff out. So we'll probably get it. Conceptually, what's problematic, or what's problematic with saying we're looking at sort of sweeping. So we're netting all variance in the extraction of these factors. Yeah.
Well, your error variance won't be related, if you're looking at an underlying construct, your error variance won't be related to it because it's just an error. And your unique variance also won't be related to it just because it's spelled out as a specific item.
Exactly.
Rather than a whole lot.
Right, and you're right on, right? So the problem is if we're saying conceptually, right, that there's some underlying factor, there's some process, there's behavioral inhibition, or sort of some other construct that's giving drive to these variables, then by definition, the only variability that we should be interested in is the variability that's shared with the other items, right? Because if there's variance in these items that isn't shared with anything else, or error variance, that can't by definition be part of sort of this component or this underlying factor that's driving things, because I can't have my common factor driving shared variability and also unique variability just for this one item, right? And so this is the problem with our principal components, and so one of the reasons why this is not technically a factor analytic technique, because we're just looking at components, we're just sort of making sausage here, right? What we want to do then, if we're going through and running a pure theoretically consistent analysis, what we should be interested in is going through and not looking at all variance, analyzing all variance, but only looking at that variance that's shared across our items, because the variance that's shared across our items is going to be the stuff that we should be able to reasonably attribute to some common factor that's giving rise to observed scores. And this is where our principal factors comes in, okay? With principal factors, and SPSS is referred to as principal axis factoring, what we're doing is we're not analyzing the full correlation matrix. What we're doing is we're analyzing a reduced correlation matrix, where instead of ones in the diagonal, instead of looking at all variance in each item, what we're doing is we're only looking at shared variance here, okay? And if we're talking about shared variance, we're talking about covariance, right? Total covariance of items with everything else, right? And so if 100 of the variance in item 1 is shared with all other items in our analyses, then we'll have a 1 for our covariance, right? But that's never going to be the case, because we're always going to have at least some random stuff and some unique stuff going on. And so what we have in the diagonal of our reduced correlation matrix are commonalities, okay? Our commonalities are only the shared variance that we have with other variables in the model, and so as a consequence, this is no longer conceptually variance, but covariance, right? The extent to which item 1 varies with item 2, item 3, item 4, so on and so forth. So whereas our principal components analysis is an analysis of variance across items, our principal factors analyses this is going to be an analysis of the covariance across items. And this is exactly, Sean, what you were saying. It's getting only, we're restricting sort of the parsing of covariance down to just the stuff that's shared with other items that are only unique to this item, that it can't be attributable to our common factor, because our common factor should be driving all of the stuff that we have moving up and forward, okay? And so again, aim at principal factors, identifying underlying processes, driving variation in our observed scores, and sort of again, unique variance, error variance for any given variable can't be directly attributed to our common factor, and so that's going to get excluded. We're not going to take a look at that, okay? So if we think about this, obviously our shared variance, our covariance is always going to be less than the total available variability in R. And so because we're omitting unique and error variance here, we can go through and extract. If we're running a PCA and we've got 10 items, we can extract 10 factors and perfectly reproduce our correlation matrix, right? Because by the time we get to factors 7, 8, 9, that might just be capturing just unique variability attributable to one item and just representing that, right? If we go through in a principal factors, we can go through and extract, if we've got 10 items, we can extract 10 factors. It'll approximate our original correlation matrix, but it won't perfectly reproduce it, right? So we're saying, hey, we're gonna be a little bit picky. We're not interested in sort of everything that goes into the sausage pile. We're all looking at this specific stuff that's going to be, we can determine as a function of our common factors. Okay, people see conceptually the difference between these two techniques and why we may prefer one over the other. Okay, so wanted to go through sort of quick overview of commonalities. So if we're going to run principal factors, what we need to do is first is get some estimate of commonalities in this. Yeah.
I'm sorry. Is there a reason why? Is there ever time when you use principal components?
Yep.
instead of-
Yep.
Okay.
We're going to start with principal components.
Okay.
If we're going to say, hey, how many factors should we extract?
Yeah.
Right? Let's start with principal components. Right? Principal components is going to go through and say, hey, this is probably going to give us the upper limit. Right? This is the top that we would want to go through. We're going to run a principal components analyses, go through and say, all right, so this is probably going to be sort of give me a beat on the number of or the number of solutions that I want to explore, then jump back into principal axis, and then go through and start taking a look at covariance there. Okay. Estimating our commonalities. So this is an iterative procedure within the guts of SPSS. Typically what's going on to get these commonality estimates, what we'll start with is a squared multiple correlation of each variable with all other variables in the model. Basically, if I take item 1 and regress it on all other variables, my R squared is my indicator of my commonality initially, right? And sort of going on and so forth. But we're going to go through and adjust these parameters as we go through the solution. Final commonalities given is an H squared. This is going to be the squared multiple correlation of each variable with the extracted factors. Okay, so by the time we get to our final commonality estimates that we see in SPSS, what this is at a technical level is if we take this item and regress it onto our unobserved factors, the proportion of variability in this item that's being accounted for by however many factors that we've gone through and extracted. Okay, again, do we want these commonality estimates to be high or low? What do you think, Zach?
I think it seems like you want
Well, if it's a proportion of variability, right? So I've got item 1, right? Do I want item 1 to be, do I want sort of my 3 factors to count for a high proportion of variability in item 1 or a low proportion of variability? A high, right? So we want high commonalities. High commonalities are telling us that our indicators are good, our solution is good, right? Because at the end of the day, we're saying that these are good indicators of the underlying construct, right? And so if this is a good item, my solution should do a nice job of accounting for variability within that item. Okay, and so again, if we're thinking about what an EFA looks like from a diagram standpoint, here we got say 6 indicators. We've got Q1 to Q9. Sort of set these up. We're thinking that each one of these indicators represents a unique construct, right? If we were doing a CFA, right, this is a more constrained version of an exploratory factor analysis. We'd say factor 1, factor 2, factor 3. Each one of these factors is driving variability in this set of 3 scores, right? And so this is what we would see in our CFA, along with some correlations between these factors probably, right? But with an EFA, what we do is each one of our factors, each one of our items has loadings on all of our factors, right? This is our CFA. This is much more constrained. EFA, much less, where we're seeing that for each factor, each item we have in our set has a loading on each factor that can be something that's sort of might be 0, but it could be something greater than 0. And so within this set, what should we expect? What would we hope would happen if we've got a good, nice, clean factor structure within our EFA? Is there any idea? How should these items relate to these individual factors? So,
each individual.
Yeah, so what should so if I'm looking at item 1, what would I hope if I've got a nice clean factor structure? What should the loadings for question 1 be with respect to factor 1, factor 2, factor 3?
High. Only for like F1.
Exactly, right? We would hope that item 1, if it's an indicator of factor 1, has a high loading for factor 1, and then what about 2 and 3? Less, right? Less or low, right? And so if we've got our CFA says question 1 is unrelated to factor 2 and factor 3, except for through correlations between these factors, right? EFA says no, we're just going to have all these factors load on, or all these items load on all these factors. But what we're hoping for in a nice clean structure is that we get strong loadings with the factors that we hope. Less loadings, lower loadings with the factors that shouldn't be directly driving that question. But if we're looking at our commonalities, what we're doing is we're regressing for commonality for question 1. We're regressing factor 1, factor 2, factor 3 onto question 1. The proportion of variability in question 1 that's being accounted for by these 3 unobserved factors, that's going to be our commonality estimate. People get a sense for commonalities, kind of what these are, sort of, and again, it's not a bad thing to think about this in like linear regression terms. This is all GLM stuff, right? And so thinking about this in terms of, it's not exactly the same thing as linear regression, but sort of the concepts sort of carry over well enough. Okay. Questions here? All right, and then we go through. And sort of in our, depending on our rotation solution or our rotation method, if we have an orthogonal, or excuse me, or an orthogonal rotation, we're not letting factor 1, factor 2, factor 3 correlate. If we have an oblique rotation, we're saying, yep, factor 1, 2, and 3 can correlate. We'll talk about pros and cons of each one of those. Okay. So benefits of principal factors. Typically more appropriate for the type of stuff that we do in social sciences. We're generally trying to determine sort of what the underlying construct is that's driving our observed scores in our measure, but our measures are generally awful, filled with all sorts of error, not only our fault, but because our participants' fault, right? So they have different stuff coming on different days. We can't control any of that stuff, right? And so what we want to do is go through and sort of only look at that common variance across scores. And so generally for our purposes, PFA is what we're going to be looking for. But because PFA requires estimates of commonality prior to extraction, what can happen sometimes, and it doesn't happen, I don't know that I've ever actually had this come up, but it can happen, and it is more prone to different types of errors relative to principal components. So requires estimate of commonalities prior to extraction, but sort of the system does that. We're not too worried about that. Doesn't perfectly produce the observed correlation matrix. Well, I didn't expect it to in the first place, so I'm not too worried about that. Where we can get into problems if we have data that have certain types of quirks, what can happen is we can start to get wonky stuff with our PFA, right? With our principal components, we typically don't have those types of errors, and again, this doesn't happen a whole lot. But what we're going to do within the context of our best practice approach is we're going to use our principal factors for our final analyses in the estimation of our model. But what we're going to do is we're going to use our principal components to start to get a sense for, all right, how many solutions should I be looking at and exploring here? And if I have problems with principal factors in terms of stuff's not working out right, principal components tends to be a more robust approach than principal axis. But again, I would be shocked if you ever run into it if you have reasonable data that's not pushing the boundaries of sort of things you should be running these analyses on. Questions? All right. We're not going to get into this a whole lot, but in terms of thinking about sort of what's going on, you got an understanding of why things can fall apart sometimes. We've got two matrices here. We've got matrix M and matrix N here. Matrix M, rank of this matrix is going to be indicated by the maximum number of linearly independent vectors, right? If we're talking about linearly independent vectors, so what we're saying is that there's no constant that we could add to any single element of one vector that's going to go through and perfectly reproduce the second vector. So we're going to identify the maximum possible rank as the lesser of the number of rows and columns. So here we've got 5 rows, 2 columns. The max rank of matrix M is going to be 2, right? And if we go through and sort of plot these out, right? So if we take 2.27, 38, 53, 62, and 15 and plot them out on this grid, right? We get different lines going through each one of these. And so we're going to say that matrix M is to be full rank because vector 1 is unequal to any constant that we would add to vector 2 and sort of perfectly reproduce it, right? So we're good here. But what can happen here, if we take a look at matrix 2, we've got something going wrong here, right? Turns out that if we multiply every element in vector 1 by a constant of 2, we get sort of vector 2, right? And so what ends up happening is we have this matrix is not of full rank. And if we plot this out, we can see we don't get sort of different scores. We get everything falling on a straight line, right? So this is a problem with collinearity within our data. So we've achieved a singularity. Our matrix isn't full rank. When you get this type of stuff, this can come crashing down and cause you problems in terms of your analyses, okay? Any idea when we might see this type of thing? So when we might have problems with matrices that are not a full rank, or what we would call singular matrices. What's that? No, not only one factor, because we're still getting things going. So when it happens, you'll know why it happened. So if I go through and just dump a bunch of, so I've got a sort of a measure, and in my data set I've also scored my measure, and so I've got a total score that's the sum of sort of all of my other basically items, and I accidentally dropped that into my analyses, right? These are the types of things that can go through and start causing problems, right? And so I go through and I get a big old fat error term in terms of going through, wanting to make sure that we don't have collinear data going in there. Most generally, if you produce a singularity, it's because, at least in an EFA standpoint, it's because you've got some variable in there that's sort of just a transform of a constant of another variable in there. But if your items are, this ends up being more of a problem when you get into more complex CFA types of things, where you've got factors that are too highly correlated, and then all of a sudden you get something called a non-positive definite matrix, and you have to go through and figure out what's sort of correlating above one with something else. But again, sort of basically, this is a matrix version of dividing by zero, and it causes problems. So just want to know that that's a possibility. And so if you see literature talking about matrices that are not of full rank, they're singular matrices, it's just saying that some vector within that matrix is an exact replication of another one. Sort of think about this in terms of matrix languages, problems with collinearity. Eigenvalues, eigenvectors, your linear components, right, that we've been talking about. Technical term for these is eigenvalues, eigenvectors. We're not going to get into this too much, just wanting you to know sort of kind of what these things are. Sort of variance associated with each extracted component in your PCA or PFA given as your eigenvalue. So when we go through and we take a look at your SPSS output, you'll have eigenvalues. This is just your package. This is the this is your unit of variability, variance or covariance that's accounted for by your first component. Your second eigenvalue is the package variability that's attributable to your second component, so on and so forth. Okay. Again, eigenvalues just a form of repackaged variance, so that they don't have, like, you can't look at an eigenvalue and say, oh, that's a beautiful eigenvalue, that eigenvalue sucks, right? But just knowing that that's what's going on. Your eigenvectors are your weights that you use to determine your eigenvalues. Know that if you've ever done other types of multivariate techniques, things like MANOVA or discriminant function analyses or things along those lines, it's all using the same thing. We call it different things. So we call it, in PCA we call it components, in PFA we call it factors, and so we talk about characteristic roots and discriminant function analyses and things. It's all the same thing. They're just all representing eigenvalues. We're just taking variability, repackaging it, and so basically sort of the coefficients that we're getting for our different multivariate techniques, always sort of using these eigenvalues and eigenvectors to go through and assign different weights for stuff. We're not going to worry about this. If you're going to do a lot of factor analyses, I would recommend sort of wanting to go through and at least have some general sense for sort of what sort of the math is behind it, what's going on. People might say, well, why is that useful to me? Because the computer does it all for me anyway. But when things fall apart, when things go sideways, which is always going to happen, this is going to give you a good conceptual understanding of what's going on, how to maybe fix it, and then it's also going to give you a leg up on being able to read competently through methods, literature, through texts, and be able to understand what's going on, problem solve stuff in your research. So we're going to skip through this, the math stuff, and just jump into the application of how we go through and start determining things, determine number of factors for extraction. Is that all right with everybody? Anybody have a hard desire to go through and look at matrix algebra? No? Okay, I thought maybe you did, but all right. So how do we go through in a practical setting, go through and just sort of determine number of factors for extraction? Assuming our correlation matrix R is at full rank, number of components available for extraction equal to the number of variables in the analyses. Again, as we've mentioned before, if I extract the same number of factors or components as there are the same number of variables, I'm going to perfectly reproduce my solution. I'm going to account for 100% of the variability in my data, right? Or if I were running a PFA and I were to extract maximum number of factors, I'd account for all available covariance, right? And again, so to stick this in your head, if we're talking about principal components, we're talking about an analysis of variance. We're talking about principal factors, we're talking about an analysis of covariance, okay? But again, what we want to do is to go through and summarize our associations using a limited set of meaningful factors, right? I probably don't want to have 10 factors going 30 item scale, and some joker's like, oh yeah, no, we extracted, this is a great solution, we extracted 15 factors. You laugh, right? It happened, right? People are like, oh, and this is a great solution, just look at how much my outcome. I'm like, if you don't need 15 factors to account for that, you're not, and so factors that don't mean anything and have maybe 1 or 2 items on it, it's nonsense, the stuff that people will do, right? So the question you should be asking yourself, how many components, factors do I need to reasonably account for the relations among these data, okay? Number of techniques that we can go through and make this determination. First one, Kaiser-Gutman rule. People probably have heard this or seen it. This is the most common technique that people will use. I'll tell you right now, spoiler alert, it's horrible. Like, you should never sort of base your solution based on Kaiser-Gutman. Kaiser-Gutman says, recommends retaining components with eigenvalues greater than 1, okay? Idea behind this, and the logic isn't bad, that an eigenvalue, a component with an eigenvalue greater than 1 is interpreted as accounting for more variance than can be attributable to any single variable, right? Because if I have completely uncorrelated items, right? I've got 10 uncorrelated items, right? Literally the correlation between them are 0, right? How many factors will I probably extract to account for everything? 10, right? And if I were to look at my eigenvalue for each one of those items, if each one of those factors is accounting for all the variability in one factor, it's going to give me an eigenvalue of 1 for each one of those factors, right? And so the idea behind extracting all components or factors with an eigenvalue greater than 1 is that it's doing something above and beyond just accounting for the variability or covariance of just this one factor, right? So it's doing something more than just accounting for itself. This is the default in most statistical packages, and this is, you will see this as the sort of the most common justification for number of factors to extract in the literature. Like, across the board, it's ridiculous, okay? But this is a horrible criterion for number of retention. You retain way too many factors. Using Kaiser-Gutman alone will horribly over-extract solutions. You'll sort of extract way too many factors than you'll need. Also, difficult to rationalize cut points back. Oh, so this is I got an eigenvalue of 0.98, so I'm certainly not going to keep that factor. But I've got an eigenvalue of 1.02, so definitely need to keep that one. So these are two categorically different things, right? At best, Kaiser-Gutman should be sort of approximate of the maximum number of factors for extraction, right? Because even if I have completely random data, there's still going to be some relations in there, right? And so, in theory, not a bad idea. In practice, the worst. Sort of just recognize that as you're going through and evaluating stuff and looking at your own. So, other thing that we can do, so this is eigenvalues greater than 1. Another thing that people will do is create scree plots. Scree plots, basically a graph of your eigenvalues across your components, right? So here, first component has an eigenvalue of 5.5. Second component, an eigenvalue of about 3. Third component has an eigenvalue of 1.5, so on and so forth across our individual items, right? So still basing this on eigenvalues, but the idea behind the scree plot is we're going to look at this for changes in the pattern, right? We're looking for some bend or break that suggests that once we hit this point, after that, we're just kind of picking up scraps. We're just getting crumbs and random variability that's not necessarily meaningful. So here we've got eigenvalues plotted in descending order, looking at determining the number of factors by the bend or the break, okay? Trent, how many factors should I extract based on this scree plot? Why do you say 3?
took everything else, it's pretty much held together.
Okay, why not 4? I mean, we got sort of this, then we drop down to this one. Did we say 4?
I mean, it's all subjective. based
Yeah,
on
maybe
this.
4, right? Probably 2 is, that's an under extraction. We need more than 2, right? And so again, we're looking here at so the magnitude of our eigenvalues, but it's giving us a plot. What we probably want to do with our scree is take a look at this and start to get a range of factors that I'm going to go through and subsequently explore. If I'm looking at this scree plot, I'm probably going to take a look at a 3 and a 4 factor solution, just to explore that, right? You can say the break is here, and then things kind of trail off after here, but I don't know, maybe I'll extract that one, see what's going on, right? And so, again, subjective than Kaiser-Gutman, because Kaiser-Gutman says if it's above 1, we keep it. This, a little more subjective, but again, a nice way to go through and say, and sort of justify the number of factors that you're exploring in a publication or a thesis or something like that. Say, here's a scree plot. So it looks like the bend is right here. We're going to go through and we're going to take a look at a 3 factor, a 4 factor, and then a 5. 5's probably an over extraction. We'll check it out and see what goes on. Right? So this is your scree plot. But again, some ambiguity here. Another technique, and this is one I like to use because it sort of helps to make things a little bit more objective. Again, something that we refer to as, labeled by Horn as a parallel analysis. So with Kaiser-Gutman, again, the idea is that we shouldn't be extracting factors that are accounting for less variability in our data than what we would account for by one single item, right? So again, not bad. But the problem is that we get random associations, right? If I were to go through and generate a completely random set of data, my items aren't going to be correlated 0, right? If I run a correlation matrix, so the correlations aren't going to be 0, they're going to be something. They're probably not going to be large, but they're going to be something, right? And so the idea behind parallel analyses is that what we're going to do is we're going to say, all right, what we want to do is we don't want to go through and extract factors that, based on sort of the parameters of these data, would be associated with less variability than what we would expect to just be occurring at random, okay? And so with parallel analyses, what we do is we go through and we plot our eigenvalues from our actual data against a data set of similar size and metric, but made of completely random scores, right? So what we do is we get our eigenvalues from our principal components analyses, right? And then we go through and we're going to run a series of principal components analyses on sets of randomly generated data equal in size of the sample study. So I got 300 people in my analysis and 20 items. I say, okay, SPSS, here's 300 people. Generate random scores from whatever the range of individuals' scores can be for an item. So let's say they're people can score between 0 and 10 on an item. And I tell SPSS, all right, in this set of 300 people, for items 1 to 20, generate a random value between 0 and 10 for each one of these, right? And so we generate a random set of data, and then we perform a series of principal components analyses on those. And then what we would do this sort of maybe 10 different times, something along those lines. And we would plot the eigenvalues from our actual data against the average eigenvalues that we would collect from across, say, a random set of, say, 10 principal components analyses. And the idea is that if this is the scree plot from our data, and this is the scree plot that we would get on average from just a randomly generated set of numbers of equal size and parameter to my original set, that I probably shouldn't be extracting more components than I would expect to get from just randomly generated data, right? So within the context of parallel analyses, what we would do, eyeball our randomly generated set, and then sort of identify max number of components to extract based on the stuff that's sort of not extracting more than what we would get from a random set, right? So again, in this example here, we might say 4 is the max, maybe 5 if we wanted to be generous. But again, this is exploratory factor analyses. I'd probably here look at a 3, a 4, and a 5, and just test those out and see what happens with those. People get the logic behind parallel analyses? All right. Other thing we can take a look at is incremental variance, right? Every component that we go through and extract is going to account for some proportion of variability in our overall set. So again, with 10 variables, we could go through and extract 10 different components. We'd have 10 individual eigenvalues, right? But if we're going through, we're taking a look, eigenvalue associated with third component 1.5 would be associated with 15% of the data, the total variance in R. But if we go through and let's say we've got, want to take into consideration relative contribution, right? So what's my cost for adding another component, right? Am I getting my money's worth? So let's say first 4 components, I'm accounting for 38, 15, 10, and 1.5% of the variability. I might not be inclined to extract that 4th component, even if it does fall marginally above my sort of random variability line. I might say, well, I would go from 38 to 15 to 10 to 1.5. That's a pretty big jump. I don't know if 1.5 a proportion of variability, so 1.5% is worth the complexity of adding on a new component. And this generally resolves itself because that one factor accounting for 1.5% of the variability generally won't be well defined by items and won't make a whole lot of sense in terms of things. But using this as another consideration in terms of how to justify the number of factors that you want to retain in terms of as you move forward with the PFA stuff. Okay, and then this is the big one, interpretability. Okay, theoretical, conceptual importance, interpretability should be your top priority, right? I don't care if you've got a eigenvalue of 3. If you can't make any reasonable interpretation of the items that load on it, that's probably not a reasonable thing to incorporate, right? We've got factors contributing non-trivial variance regularly don't have any type of substantive meaning. We start to see uninterpretable, unreliable factors if we have a factor that's marked by a bunch of weak loadings, right? It just has items on it, but none of them are very good. They're all in like the 0.4 range. We see complex loadings. We see, we extract that 4th factor. That 4th factor doesn't have any items that clearly just load on it and not load on other things, right? This 4th factor is completely made up of items with complex loading. It's got a loading of 0.5 on the 4th factor, but 0.4 on every other thing. I don't have a good sort of conceptualization what that is. Items having little conceptual cohesion, right? Sometimes we get just the math, and from a data standpoint, we get, okay, these 4 items are holding together, but I have no idea why. These are completely different items. There's no reason for these things to start holding together. Now, you might want to put on your thinking cap, think a little harder and try and account for that. But if there's no good conceptual accounting for why these variables should be, or these indicators should be existing and holding together, probably not strong justification for retaining that. And then this is the other thing that you want to do and be very, very careful about this. We start to see items within an EFA starting to load on a similar factor, not because of sort of the underlying concept or the underlying construct, because of something about the item, right? So I've got a bunch of items that are worded similarly, right? I've got items that have a similar scaling, right? If I'm factor analyzing sort of items from different scales all on the same thing, these items are on a 0 to 10 scale, and these are on a 4 or a 5-point scale from 0, 20, 40, 60, 80. Now all of a sudden I'm getting items that are loading just on this because of the scaling issues. Similar difficulty, if we have certain items that sort of like say in some sort of cognitive assessment that just aren't tapping into the construct, they just all happen to be more difficult, we can start to get loadings there. Or if we have missing values, right, and we've gone through and mean substituted for a bunch of stuff or used some imputation procedure, we see that the items that have a lot of imputation are all loading on the same factor, right? So lots of reasons. As you're going through and so once you've got your solution, always wanting to make sure that you don't have something from, you want to make sure that what's driving the, sort of these scores holding together is not because of some methodological issue, it's because there's a real sort of underlying construct that's driving variability in those scores. Best case, or the best example of this, and this happens all the time, reverse coded items, right? I've got an item on a scale. I've got a beautiful two-factor scale here. We've got sort of this is this and that's that, and you go through and take a look, you're like, oh, but I'm also noticing that all the straightforward coded items are on this scale, all the reverse coded items are on this scale. You don't have two factors, you just sort of, the analysis is just separated out, sort of people who are responding to the reverse coded items versus the straightforward coded items, right? This would be a methodological issue that you would want, because it's embarrassing to say, to crow your explanation for this beautiful two-factor solution that you've got, and then you get me as a reviewer and like, yeah, no, these are reverse coded items. You don't actually have anything real there, right? And so also not wanting to sort of retain an under-extracted solution, because you don't want to try and have to interpret other stuff. But in general, this is going to be one of your most important considerations as you're starting to go through and determine scores. Okay. How are we doing on time? What time is it?
3:30.
What?
3:30.
All right. How are people doing? People need to stop, take a break? All right, well, we'll keep going. Someone raise, flag me down if you need to sort of restroom or something like that. All right, rotation procedures. Again, as I talked about before, rotation is just repackaging your variance. We're just going through and shifting things around. Rotation doesn't improve the fit of your solution. Your fit of your solution is the fit of your solution. Rotation doesn't do anything with this. Rotation just repackages your variance, covariance to help start aiding interpretation, right? Law is conservation, right? So it's the same solution. Rotation doesn't change your solution. Rotation just helps go through and make some interpretations. You'll hear people talk about simple structure in factor analytic stuff. Simple structure is what we will use to sort of say, yes, this is a good solution, or a confusing solution that doesn't have a strong interpretation. We say that a solution is achieves simple structure when our factors are defined by several variables that correlate highly and uniquely on that factor, right? So like you were saying, Sarah, what I would hope for if I'm running this EFA, if I've got a good solution, I've got indicators that are clearly mapping onto these underlying constructs, I should have each one of my factors defined by a nice collection of indicators that have very, very high loadings on this factor and sort of minimal loadings on the other factor. We would say that this is achieved simple structure. If I've got items that aren't loaded very highly on any factor, or items that are loaded sort of highly on multiple factors, this starts to get complex and will be a non-preferred solution relative to sort of things where everything's loading cleanly on stuff. And so, again, we're going to evaluate this based on plots, loadings in our rotated loading matrix. Two types of rotations. We can have our orthogonal. This is uncorrelated rotation. Oblique is correlated rotation. Uncorrelated rotation specifies that our underlying factors in their true form, right, are uncorrelated with one another. They're orthogonal, they're at right angles. Our oblique rotations allow those factors to become correlated. Our oblique rotations complicate solutions a little bit, but are advantageous for other reasons. Some things we want to take a look at with that. So thinking about this geometrically, okay? Let's say in this graph here that our axes here, axes 1 and 2, these are our extracted components, our extracted factors, okay? Our individual dots here are the loadings for our individual variables, okay? And this is literally the geometry underlying factor analysis. This is like a real thing, right? Just not just a demonstration. What we would do with this, I mean, this is a two-factor solution here, right? The vector that we get from the origin of these points to the individual points out here, gives us the commonality for our variables. So our vectors that have greater length indicate greater proportion of variability, or variance covariance attributable to that solution. Okay. So Tess, I don't know if you can see this here, but so which one of these items, this item or that item, has a higher commonality? Sarah? The longer one, right? So again, the length from geometric, like literally the length of that vector is going to be a mathematical representation of the commonality. And what's commonality, Steph? What's that? Yeah, overlap with factor. Yeah, is a proportion of variability in the outcome that's attributable to sort of both of these solutions, right? And so if we have these values hanging out higher on the ends, where if we were to draw a vector from the origin of our coordinate plane here out to individual dots, the length of that vector is going to be representative of your commonality. So the longer, the better. So the stuff in here towards the origin, those are items that we're not doing a very good job accounting for. The items that are farther out, stronger commonalities there, okay? Also within this context, physical proximity of a coordinate to the axis indicates a relationship with that specific factor, okay? And so technically what we can do is we can actually start to calculate within this system actual factor loadings based on the angle between this vector and the coordinate, where we actually just start taking the cosine of that angle and start to actually calculate our factor loadings here, right? So in this case, we would have this item down here would have high commonality, right? And probably a high loading with factor 2, right? And not so much of a less of a poor loading with factor 1, right? This one right here near the origin, though, poor commonality is a very short vector, and it actually is running about 45 degrees in between these, right? And so it's pretty equally loading on factors 1 and factor 2. We've got kind of a complex loading with a poor commonality. This isn't a good item. This is an all right item, okay? So if we're looking at this, are we happy with this solution? Sean, you're looking skeptical. Why are you looking skeptical?
Well, you have three things in the middle that aren't very good.
Mm-hmm.
So, in terms of rotation, you try the orthogonal rotation first, and then see without the correlations, which ones will which factors.
Okay, so a couple of things here. You're on the money here, right? So we're not super excited about this solution because we've got some things going on out here that sort of are kind of intermediate between our two factors, right? So they're probably going to be loading strongly on, or so at least reasonably on both of these factors. And then we've got a cluster of points here that also are kind of, they're not sort of on the, we want our sort of points to be kind of clustered around our axes, right? Because that would indicate strong loadings. And then we've got these jokers in here that aren't doing much of anything. But we do have, because our axes are at right angles to one another, we do have an orthogonal rotation here. So if this is our extracted solution, what we can do with our rotation is we just take that axis and we shift it, right? We literally rotate that axis around. And so if I look at this solution relative to the unrotated solution, now what am I seeing, Sean?
You're starting to see it better. You're a little bit more happy with the design here.
Yeah, why is that? How do I see that I'm happier with this?
Because your first vector, the factor 2 that goes up, factor 2 and factor 1, you have points that are clustered around the line.
Exactly, right? And so this geometrically is what's going on with our rotation procedures. It doesn't change the solution. The solution is the solution, right? What we're doing is we're just shifting things around so that these items that are kind of hanging out together in the same sort of geometric space are now clustered around the high end of factor 2. These ones are now clustering on the high end of factor 1. Before, right, these were probably sort of around factor 2, these ones are around factor 1. Now we just sort of switch those around, and so these are all on factor 1, these are on factor 2, right? And this is important to recognize. Sort of the ordering of factors and things is sort of arbitrary, right? I mean, sort of your components will come off. The one that extracts the most amount of unique variance will be the first, and then so on and so forth down. And so you may have solutions where, let's say I run an EFA on a measure I'm developing. And I say, all right, factor 1 is this, factor 2 is this, factor 3 is this. And then so I say, all right, I want to replicate this to see if I can do so. I collect a whole new set of variables, or excuse me, a whole new data set, and run it again. And I'm getting the same things. It's just this time, factor 2 happens to be factor 1, factor 1 happens to be factor 2, and factor 3 is still factor 3. That's fine. That doesn't mean anything. This just has to do with sort of sample-specific stuff, the rotation of this. And so this is just an interpretation from a geometric representation, what's going on with this rotation, right? So our eigenvalues don't change. It's just helping us interpret these a little bit better, okay? If we're going through and we're taking a look at sort of our plots, again, this is a very simple two-factor solution. This would be an example of something in an EFA we would probably identify as simple structure with our orthogonal rotation, right? We've got these people sort of loading high on the end of factor 1, these people high on the end of factor 2. These items aren't really doing much of anything, but if it's an EFA, we're developing our own measure, what do we probably do with those? Get rid of them, right? Those aren't doing much of anything, so we're just going to get rid of them. Now, also what we might do here, and probably what's going on, is we might have a 3-factor solution here, right? How do we see a 3-factor solution, Judah?
Go back to our screen plots.
Okay, we could. Geometrically though, right? So we've got factor 1, right? We've got factor 2, but then we've got these ones kind of hanging out right here at the origin. If we add a third dimension to this, those ones might be hanging out if we sort of open this up in the 3-dimensional space, could be hanging out here, right? And so because these are looking like they're all kind of clustered together anyway, right? What may happen is if we add another dimension on that, we may get sort of these guys hanging out here in 3-dimensional space, these guys up here, and these guys way out at the end here. In 2-dimension space, there's nowhere for them to go, so they're just kind of camped out in the origin, not having sort of a strong commonality of much of anything going on. But the clustering of these items would suggest maybe there's a 3-factor solution going on there. Same thing, if we go down through and let's say that we've got sort of a group of items hanging out here, a group of items hanging out here. This might call for an oblique rotation, right? What we're doing with an oblique rotation is we're allowing these factors to correlate. So our dimensions don't have to be at right angles to one another. They can be sort of at some acute angle here. And so instead of an orthogonal solution, we've got sort of this factor going here, this one going here, and then maybe this one orthogonal to the other two again hanging out here, except for this time we've got sort of correlated factors with a third factor up. Here, we might have a third factor or maybe even a fourth factor, but here we've got sort of 1, 2, another guy going on. So this is a group of items that are going to be sort of cross-loading between factors 1 and 2, right? So maybe we could use a third factor there. Here, no simple structure. We've got items that aren't correlated at all with one another, and so no grouping or clustering with that. So people kind of getting an idea from a geometric perspective, kind of what this looks like in terms of rotations. I mean, if we get beyond 3 factors, it starts to become difficult because we're in 4-dimensional space, and that's hard to think about. But generally, sort of getting a sense for what this rotation stuff is looking at. Yeah.
When you do this, is this 3-dimensional or 4-dimensional?
That would be 3. So we've got 3 axes here, right? So we have 1, 2.
So
3
then
axes.
what's 4-dimensional?
Time, I guess.
Forever.
Yeah, it gets into the sort of stuff that's interesting, but hard to represent in our three-dimensional world, so we won't worry about that here. But just know, sort of this is just an extension of some of the stuff that's sort of 1 and 2 dimensions here. So pros of our orthogonal rotation. Orthogonal rotation is easy. It's straightforward. Basically everything sums to 0. Our factor loading matrix that we're going to get in SPSS, it's just going to give us the unique correlation between our observed variables and the factors, right? Literally, how is our factor correlated with our individual items? And there's some matrix stuff that you can go through and do on your own if you like. Cons of our orthogonal rotation, not likely to reflect reality, right? Unless you really think that these sort of factors are truly uncorrelated with one another. Now in practice, it is rarely has a huge impact if you've got a good clean factor structure, but from a conceptual standpoint, you're saying that the components or the factors that I'm extracting are uncorrelated with one another, which isn't map on nicely to probably most of the stuff that we're doing. Again, it's not often that you'll have a measure that you say, oh, it's got 3 subscales or measures 3 different factors, all of which are unrelated to one another. Not to say that it doesn't happen. I've got sort of a measure out there that we put together that actually, they're not uncorrelated, but they're very weakly correlated, right? To the point where you wouldn't say, oh, let's sum these all up and create a total score, because they look like they're distinct enough things. But sort of one of the problems with orthogonal rotation. Varimax, most common. What we're doing is we're just maximizing variance of loading within our factors across variables. With Varimax rotation, variables with stronger loadings tend to become a little bit higher. Those with weak loadings become weaker. And so with our Varimax rotations tending to reproportion variability so that our factors are of relatively equal importance. Obliques, our oblique rotations, sort of this is doing a better job of capturing correlation, theoretical correlations between our underlying constructs. But it makes our solutions a little more complicated. Not everything sums to 1 within the context of our oblique rotation. We get multiple loading matrices within our oblique rotations. Our pattern matrix, which is what we'll go through and use to go through and interpret, looking at unique relations between factors and variables. But again, what we're doing here with our pattern matrix is it's looking at, instead of correlations, these are more like regression coefficients, right? So what is the unique relation of, in our pattern matrix, what's the unique relation of this item to the other factors controlling for, to this factor controlling for relations with other factors? Helps with interpretability, but it's not a straight correlation that we're interpreting here. Structure matrix, this is the correlation between factors and variables, we'll talk about that. And then with our oblique rotation, we're also going to get a factor correlation matrix. It's going to tell us how correlated our individual factors are that we've gone through and extracted. Promax, most common. It allows correlations between factors but doesn't require it. And so if you do have truly orthogonal factors, you can just estimate those at a correlation of 0. But again, small to medium loadings push towards 0. Larger loadings reduce to some extent within these, because you're going to have some of the variability peeled off and correlated with other stuff, but not too bad. Okay, so choosing a rotation, orthogonal, even though it doesn't map on, it's generally the most common that we see in the literature. Gives us a parsimonious model, especially in truly exploratory stuff. If it's truly exploratory, you really don't know what you've got, which is kind of a weird thing, because you probably have some idea to start out with, or some guesses. You can make arguments for oblique rotations if you know that sort of this is going to be related to this. We've got more accurate reflection of processes, but so you want to make sure that you know what's going on interpreting these solutions adequately. Also want to be aware of the correlation between your unobserved factors, right? This gets into issues of discriminant validity. I'm not going to say, oh, I've got 3 factors all correlated at 0.9 with one another. Measures of the same thing aren't correlated at 0.9 with one another, right? So you don't have unique factors. You have the same factors that you've parsed into sort of smaller bits and pieces. Anytime we get factors exceeding correlations of 0.7, 0.8, probably have some redundancies and things. And so if you're going to specify an orthogonal, or excuse me, an oblique rotation, wanted to be paying attention to sort of how strongly those factors are related to one another. But if I've got a good stable solution, you're generally not going to see probably a lot of difference across an orthogonal rotation versus an oblique rotation. It's probably going to be pretty similar, right? You get some sort of variation. If they're similar, then you might go with the one that makes the most sense, or the most simple one. But if you've got a good simple structure, things shouldn't make too much of a difference here. Okay. Let's go through, we'll push through sort of commonalities in this next thing, and then we'll stop, take a quick break, and then jump into SPSS stuff. Okay. Commonalities, again, this is your proportion of variability in your observed indicator that's accounted for by all of your extracted factors or components. Your commonality, think about this as your R squared, right? Regressing your individual item onto your unobserved factors or components. H squared, or your commonality, given the sum of your squared loadings across all extracted factors. Asterisk, unless you're working with an oblique rotation, then it's not, right? But your orthogonal rotation, if I take my factor loading for factor 1, factor 2, factor 3, and I square those factor loadings and add them up, I'm going to get the commonality for that item within an orthogonal rotation. Your uniqueness, this is identified as your proportion of variability not attributable to your common factor. So 1 minus your commonality is going to give you your uniqueness, right? This is the proportion of variability in your indicator that's not being accounted for by your solution. Do you want uniquenesses to be large or small, Trent? Your uniqueness? So this is the proportion of variability not being accounted for by your solution.
That's small.
Mm-hmm. Because again, if I put together this measure specifically to tap into this construct, I would like sort of my solution to account for a big proportion and sort of not have much left over, right? This is your error term in CFA. This is a little round thing that goes pointing down onto your indicator. Your uniqueness in and of itself, composed of a couple different units. Your unique non-error variance. This is going to be your systematic variability that's not attributable to the factor, but it's attributable to something else, right? There's something in this factor that's causing some systematic differences. We're not accounting for it by this factor, or this item has some systematic variability that's not attributable to the factor, but it's attributable to something systematically different. Maybe it's gender, right? Maybe men and women respond to this item differently. Now the factor's not catching that, but it's some systematic variability that could be accounted for if we sort of get gender as a variable in this solution. And so we would calculate our unique non-error variance as our reliability minus our uniqueness, right? So if our reliability of our measure is 0.8, or the square of our reliability estimate is 0.8, and our commonality is 0.7, that suggests that there's some 10% of variability in there that's attributable to something that's systematic, that sort of remains constant across time. It's just not being picked up by our factor. Okay? Our error variance then is our systematic random error variance associated with the measurement error. This is 1 minus our square of our reliability. And by reliability, I mean test, retest probably is the best estimate. Our internal consistency is limited in terms of its use here with this stuff. So factor loadings, okay? Factor loadings, this is what we're going to go through and take a look at to try and make some reasonable interpretation of our solution. Factor loadings can be interpreted as the unique relation between an item and each latent factor, okay? Again, asterisk, if we're thinking about an orthogonal rotation, this is nice. What's about orthogonal? Orthogonal rotation, our factor loadings indicate the exact or the correlation of the item with the underlying factor. So in this measure, we'll go through and sort of run through this in SPSS. A special person's around when I'm in need correlates with factor 1, 0.289, correlates with factor 2, 0.214, and factor 3, 0.87827, right? If we square these and add them all up, what do we get? Sarah? The commonality, right? Again, in the orthogonal rotation. Now, in our pattern matrix, if we have an oblique rotation, these factor loadings are going to represent the unique relation of each of the item with each one of these factors, controlling for sort of shared variability across them, which complicates things a little bit. But what we want to do is go through and start to identify items that have significant or salient loadings on a given factor. Comrie and Lee have a very influential text here, identified factor loadings of 0.32 as poor, right? If we go through and we square that, we get 10% of the variability is attributable. 10% of the variability in this item is attributable to the factor. That's pretty poor, right? Particularly if we're developing a measure where this is an item of this underlying factor, we would hope that it counts for more than, the underlying factor counts for more than 10% of the variability. 0.45 being fair, 0.55 good, 0.63 very good, 0.7 excellent. What we want, if we're looking at simple structure, is very, very strong loadings on the factor that it's intended to load on, weak loadings on all other factors. Items where we have salient loadings on multiple factors, we're saying these are complex items. And if we're making our own item, we can get rid of them. If they're on an item on an established measure, we can say, hey, so these are sort of complicated in terms of their relation with the underlying factor. Okay. So our conceptual task here is always, when we're making interpretations, determine, so what is the construct, right? So we see these items holding together. What is the construct that's being represented by this? What is the underlying sort of process or psychological construct that's causing these things to be related to one another? Sort of one of the most fundamental components of these types of analyses. Okay. We'll go through, so this is different things. Within the context of an oblique rotation, you can go through and identify variance attributable to the factors, variance in a set of indicators attributable to a given factor, proportion of variability in the solution. You go through and take a look at that. So that's neither here nor there. I mean, it's important stuff, but it's sort of aside from, I want to get into some examples. Practical issues, like how many people do I need to sort of run a factor analysis? More is better. More is always better. These are large sample techniques. But in general, 100 to 200 people, and again, sort of the number of people you're going to need, you're going to determine on the number of factors that you have, how well defined those factors are, and your commonalities. So if you've got well-determined factors, right? I've got this factor out here, this factor out here. The items do a very good job of mapping onto those factors. They don't cross-load, and we've got strong commonalities. You can get away with 100, 100, 200 people. If you've got low commonalities, not too many factors, and small number of indicators, I've got sort of 4 items loading on each factor. All the commonalities are low, probably going to need over 300. I've got low commonalities, multiple weakly defined, several weakly defined factors. I want to sort of extract 7 weakly defined factors with commonalities of like 0.4. I'm going to need a lot of data to have a stable solution here. Assumptions in terms of normality. Technically, these are distribution-free analyses, right? So we don't have to worry about, so if I have data that aren't normal, it's technically not violating an assumption, but many of our methods sort of do better if we have reasonable multivariate normal data. Linearity is going to be an important thing because, again, sort of these analyses are ran off a correlation matrix. Our correlation matrix is assuming linear relations between data, and if item 1 and item 4 have a curvilinear relationship, it's going to degrade the estimation of that relationship. It's going to say they're correlated very poorly, when they're not. They're just related in a nonlinear fashion. And so linearity is something you want to take a look at, outliers, multiclinarity stuff, factorability. This is sort of basically you don't want to sort of go through and run a factor analysis on data that are uncorrelated with one another. We've got a couple different tests here. Bartlett's test tests that elements of the correlation matrix are equal to 0, or that your correlation matrix is equal to identity matrix. Is this anybody think that this is probably an important thing to look at? No. Or you don't need a statistical test to tell me that sort of my correlations as a whole are not 0. KMO, something that we would probably be more likely to take a look at. KMO values above 0.8 are good, above 6.0 adequate. So again, so these are just indicators of the extent to which your items are correlated with one another. And again, if we're wanting to go through and run a principal factors and we're only looking at shared covariance across a model, we tend to probably want our factors or our items to be reasonably put together. Okay. Some other stuff here that we won't worry about. Let's take a break and we'll jump into SPSS stuff when you guys get back. All right, pull up this MSPSS data set that you have in the handout. This is what we'll be working on to go through the kind of really unrealistic best case scenario set.
Best case scenario?
Yeah. Yeah.
Which one, what is it again?
MSPSS.
Is SPSS the best software to use for factor analysis? In
Yeah,
your
I mean, in
opinion?
fact, it does what it's supposed to do. I mean, it's just one of these things. I mean, it's perfectly, unless you want to do something crazy, it's going to be fine, right? Like, so at the end of the day, your statistical program has little to nothing to do with sort of the actual numbers and values you get. It's not like SPSS has a proprietary sort of algorithm that does better factor analysis than anybody else, right? So there's data issues that will come up if you're working with very, very large sets, very complicated sets, and it starts to exceed SPSS's powers. But for sort of the basic stuff, the only drawback is that they make you pay for it.
Okay.
So, but anyway, okay. So people have this data set up and open? Okay. So basically what this is, if you go through and you take a look at your handout here, this is a measure of social support that we use in our lab. All right? It's straightforward. If we go through, take a look at the sort of this measure, any idea on what we would expect in terms of factor structure from the multidimensional scale of perceived social support?
It's one factor?
You might have one higher order factor.
Can you say what was the question again?
How many factors should we expect to get out of this? Great. Yeah, why is that, Sarah?
Well, one for friends, one for family, and one for your
Yeah.
social person.
Yeah. I mean, basically, it's looking at sort of do we have support from our friends? Do we have support for family? Do we have support from a significant other, right? 12 items, 4 items, each scale. Very quick, very easy, sort of very straightforward face valid measure, right? And so what we're going to do, let's say, okay, that's all well and good, but what I want to do is I want to see if that actually sort of, if our data actually provide evidence for this 3-factor structure, items tapping into these different constructs of family support, friend support, and support from a significant other, right? So here you're going to have your data set. We've got a reasonable collection of scores, 309 scores here. And so maybe what we want to do, because you should always do this, is start out by just taking a look at distribution of your items. Again, EFA is a distribution-free analysis, but our solutions are optimized when things are playing nice, right? And so, and if we've got weird stuff going on in there, we probably want to know about it, right? So I'm going to go through, ask for the descriptives for these, and go ahead and hit OK. Zach, what are we seeing in terms of our distribution of property? Any red flags here? And we've got, so all this is on your handouts too, so if you're having a hard time seeing stuff on the board there. What's that? Yeah, you just distribute, looks pretty good, right? In general, some people are reporting very low levels of support, some people are reporting very high levels of perceived support. All our values are all within sort of what they should be. So again, might want to do sort of more in-depth thing if you want to look at item level analyses, which isn't a bad idea. But in general, it looks like things are looking pretty good, right? So what's the first thing that we want to do if we're going to go through and take a look at this scale based on what we talked about? What's our first task? What's that, Lucy?
I think it was something with a P.
Yep, we're going to do, that's the technique we're going to use. What is the purpose of that P technique?
Principal component analysis, which is
Yeah, principal components analysis. And what are we trying to do with this?
we just want to see generally, we want to extract how many factors there are.
Right. Because we're doing this exploratory, right? So someone's come up with the MSPSS and they said, hey, this is a thing. We're like, I don't know if it's a thing. I'm going to go through and see if in an exploratory fashion, how many factors the data are suggesting that we go through and extract here. So we're going to go to analyze. We're going to drop down to dimension reduction. Select factor. We're going to take our 12 items, making sure not to include our total scores in here. And then if we go down through and take a look, we're going to go through and we're going to ask, so we can ask for a number of different things, some different matrices that it'll print out. We could ask for univariate descriptives if we want. We're just going to focus on our KMO and our Bartlett's test of sphericity, right? This is just going to tell us, so to give us a general sense for whether or not these data are suitable for factor analyses, sort of hopefully that we have some correlation. Basically, if our correlations between all of our items are 0.1, this might not be a reasonable analysis to move forward with. So I'm going to click KMO and Bartlett's, continue, extraction. We're going to make sure that we're on principal components, because this is where we're just going to start out by going through and running our analyses on all variants, right, or all variability in the data, right? So we don't care where it's coming from. It doesn't have to be shared. We're just going to start with the whole shebang. We can leave the unrotated factor solution. That's fine. But make sure to go through and click this scree plot, right? This is going to give us a plot. You can see extract. It doesn't really matter for this step. We can just leave this on eigenvalues greater than 1. This is our Kaiser-Gutman rule. It's the default with this. But you see, we can go do some other stuff that we'll get into here in a moment. We'll hit continue. Rotation. Do we need to worry about rotation in this initial run? No. We're just trying to find sort of the number of components that we might want to pull out of this. So we'll leave that. Scores, this is where we can start to save actual factor scores based on different procedures. I'm not going to recommend that you do that for a number of reasons we'll talk about if we have time. And then options, none of this stuff is necessarily relevant. Down here, if you want to get a cleaner loading table, you can go through and suppress small coefficients. So if you don't want to see loadings that are less than 0.2 or something along those lines, you can go say, hey, don't show me anything less than 0.2. But again, if I have crummy loadings, I want to know why they're crummy, so we'll leave that there. Okay. So then what I'm going to do is I'm just going to hit paste. Run this. All right. So, in our output, First thing we get is KMO and Bartlett's test. Our KMO is giving us a value of 0.883. Again, anything above 0.8 we considered excellent. Anything above 0.6 we said was adequate. So this is good, right? It's suggesting that there's covariance among these items that are worth running through a factor analysis. Our Bartlett's test is telling us that our correlations in our diagonals are significantly different than 0 as a whole, which is not terribly useful, so we're going to go through and ignore that. I mean, if that was not significant, then that would be something, right? But that's never not going to be the case, particularly if we're working with large samples that we should be working with factor analyses, right? We're going to go through, take a look at the commonalities. Now, commonalities here are going to be a little bit tricky, and you don't want to put too much emphasis into this, because basically this is telling us, so the proportion of variability on our individual indicators that are being accounted for by all components with an eigenvalue greater than 1, right? Having not proceeded down yet, I don't know how many components it's extracted, but in general, if I'm just looking at these are very nice. These are very, very strong communalities, and so I'm at least encouraged, okay? What about, what's this column of 1s right here? Anybody have an idea? Remember that because this is a principal components analysis, we're extracting total variance in our outcome, and so this 1 is our initial variance, because we're getting 1 unit of variance across all of these, right? So this is just the 1 that's going along the diagonal of this correlation matrix. Okay, we'll go down through and take a look at our next table. This is our total variance explained by the number of components extracted in this solution. We see that it extracted 3 eigenvalues greater than 1, and that the extraction of 3 components is accounting for over 80% of the variability in our outcome. Are we happy with this? Yeah, it's beautiful. Like, this never happens, right? If we go down and we take a look at our scree plot, we very clearly have first eigenvalue, second, third, and then flat, right? Everything else aside from that associated with eigenvalues less than 1, right? We very clearly have a 3-factor solution in this case, okay? We go through, and if you go through and take a look at, even though we only extracted 3 eigenvalues or 3 components for this solution, eigenvalues go all the way down. Again, we have 12 items. We can extract 12 eigenvalues. By the time we get down to the 12th component, we've accounted for 100% of the variability in our outcome, right? All this is sort of what we would expect from a PCA. But what this is suggesting here is that we've got very clearly 3 components, 3 factors. I mean, really with this, it doesn't make a lot of sense to play around with anything else, because it's sort of embarrassing how clear this 3-item solution is on this, right? So if we go down, you have your component matrix. So this is your correlation of your individual items to our unrotated components. This doesn't have much interpretive value, just because we haven't requested a rotated solution, and so outside of math and computational types of things, probably not worth taking a look at here, because again, our main purpose with this initial run is just to get a sense for how many components to extract out of these data. Okay, so we're going to say that we are going to go through and take a look at a 3-factor solution. And so what we're going to do is we're going to go up, we're going to go analyze, back down to dimension reduction to factor. Let's go to descriptives. We don't have to ask for KMO. We already know what the KMO is. That's not going to change. Continue extraction. Instead of principal components, we're going to ask for principal axis. Now you see lots of different options in terms of what extraction you want to use. If you have a good reason for using one of these other ones, fair enough, but you should have a strong justification for why you're doing it before you jump into that. So,
Can I ask a question?
yeah.
And we're doing this because we first ran principal components analysis and we saw like, okay, 3 factors is the best fit. I don't know if that's the correct language. And so now we're gonna go in and look more specifically at those 3 factors.
Right, and so what are we doing? What are we doing with principal axis here that we didn't do with get with principal components?
I don't know.
But we could have gotten that with principal components if we wanted to. I mean, I can ask for a rotating solution. What's the difference between the principal components and principal axis?
Is principal axis principal factors?
Yeah.
Oh, it's gonna take out all of the error variance, it's just gonna look at what's shared.
Exactly. We're just going to, with this analysis, so we're sort of saying best sort of far end, right? So we want to make sure that we don't under extract. What's the maximum number of factors that we would extract if we're looking at all variability in the data?
Mm-hmm.
Saying 3, okay. But what we probably want to do is, because we're psychologists, we're interested in these underlying constructs. We want to get a sense for what are the underlying constructs that are driving some of these differences or sort of causing variability. And so in that case, if we're talking about a common factor that's driving variability on our outcome, we're probably not interested in looking at variance that's sort of its own unique variance. We just want to look at the shared stuff. And this is what's going to happen when we look at our principal axis. So we're going to go down through, click on principal axis. Let's not choose screen because we already have that. That's not going to change at all. But down here, instead of just on the extraction, instead of based on eigenvalues greater than 1, let's go say a fixed number of factors. I want 3 factors. Okay. And hit continue. And then rotation. Let's start by requesting Varimax. Varimax is going to be our orthogonal rotation, and so it's going to force our factors to be uncorrelated with one another. So we'll go through select Varimax, hit continue, scores options, we don't need to worry about that. Okay, you guys can hit paste. I'm going to hit OK here, and what we're going to get is our. If I turn that on. Okay, here we go. All right. So we've got a new commonality table here. And again, what we're going to get with our commonalities in this solution is the proportion of covariance this time, right? Because again, if we take a look at our initial values here, they're not 1, right? What we're doing is we're just looking at covariance. What's the shared variability or covariance among these indicators that we're trying to account for? We have our initial here, and then we have our extraction. These are our commonalities. These are proportion of covariance that we're accounting for by the extraction of these 3 factors. And again, as we're going down through looking at these commonalities, these are very, very good, right? We should be very happy about this. When we go down through and we take a look at our total variance explained, again, we've got our 3 factors that we told it to extract, now accounting for about 75% of the covariance in these items, right? So we'll see this generally be systematically lower than with the PCA because we're just sort of accounting for everything, kind of capitalizing on chance. Here we're only looking at covariance, right? So we've got our eigenvalue for our first factor, our second, our third. We see that our first factor that we've extracted is accounting for over 50% of the variability. The second, the 13th, the third, close to 10%, okay? Why are we getting less covariance accounted for with each one of these each one of these factors? so why are we seeing less covariability in these data being accounted for with each successive factor?
We are seeing less?
Yeah. So this first one is counting for over 50. The second one 13. Third one 9. Sort of cumulative, we add up to about 75%.
Because the variability in the first two is not
Right, right. So with each factor, the first one is accounting, this first factor accounts for 50% of the covariance in the data, right? And then with the second one, we say, all right, we section that off. Now we're left just taking a look at whatever's left over, right? Then we capture that, suck that down, whatever's left over. So there's less and less variability to account for with each one of these factors. And so this is what we'll see. And so again, eigenvalue clearly above 1. But I mean, with the last extraction of this last factor, still getting close to 10% of the variability in our data, so definitely worth going through and extracting that third factor. If we go down and take a look at our factor matrix, this is our unrotated factor matrix. So again, not much use in trying to interpret much of anything here. But if we go down through and we see right below that, we have our rotated factor matrix. Okay. Here, what we've done is we've taken that factor matrix and sort of gone through and applied an orthogonal rotation. So we're taking this 3-factor solution and we're just turning it around in multivariate space until we're trying to get optimizing sort of the best sort of location in terms of where these scores are clustered. And here we start to see that we see very clear patterns, right? So we've got special person, or if we go down through and take a look at our first factor, if we look at items that are loading high on this first factor and low on the others, family tries to help me. I receive emotional help from my family, can talk about problems with my family, family willing to help make decisions. So what is this first factor that we've extracted?
Family support.
Family support, sort of perceived support from family. Second factor, we got friends really try and help me. I can count on my friends when things go wrong. I have friends who enjoy my share my joys and sorrows. I can talk about problems with my friends. We got perceived support from friends. And then the last one, special person when I'm around in need. Special person, a real source of comfort. Special person who cares for me. There's another one in there somewhere, right? We've got this significant other, some other special person, right? And so if we look, we see very strong loadings on the target factor, relatively low loadings on the others, right? Suggesting that we've achieved simple structure here. Very clean factor loading with this, where we've got strong loadings on the target factor, lower loadings on the other factor with this orthogonal rotation. If we go through and we were to take these factor loadings and square each one of those and add them up, what would we get?
Say it again?
So if we took each one of these factor loadings and squared them and added them up, what would we get? The commonality, right? If we went up to this unrotated factor matrix and squared these and added them up, what would we get? What was that, sir?
the same thing, right?
The commonality, right? Because it's the same thing, right? Sort of they all sum to the same stuff. It's just we rotate it so that we can enhance interpretability here, okay? And so this would be our Varimax rotation where we're saying, so we forced this to produce a solution where these factors are uncorrelated. Are they uncorrelated? In real life, do we expect family support, perceived family support to be unrelated to perceived friend support, perceived significant other? Probably not, right? Again, if we have support in one domain, tend to have support in the other. Not necessarily, right? But probably in generally. Also remembering that this is perceived support, like it's your impression of the extent to which others are supporting you. And so there's probably correlations associated with that, right? So maybe what we want to do is go through and run the same solution using a different rotation method. Right? So if we go back up and go to dimension reduction and go to factor, but this time in rotation, instead of Varimax, which is our orthogonal, let's choose Promax, right? And hit continue, and and then hit OK. Okay. This is just going to be the same solution. It's just going to, we're going to use a different rotation method here, right? And this is going to allow our unobserved factors to correlate, right? So this means our axes don't have to be at 90 degrees. They can be at different angles, okay? Our commonalities table with our extraction, is this going to be different than what we got before, Sean? Nope. Doesn't matter, right? We're just playing around with the extraction factor matrix. Unrotated factor matrix is going to be the same, but then we get down to our pattern matrix. Okay, pattern matrix, remember, is different than our orthogonal factor or our loading matrix, because what this is going to give us is it's going to give us the unique relation of our item with our, the unique relation of our factor with our item controlling for the other factors, right? So think about these in terms of regression coefficients instead of correlations. Again, if we go down through, we see this, even though we change our rotation method, we see factor 1, targeting family, talk about things with my family. Factor 2, we got friends, special person. So it didn't change sort of the interpretation of these factors at all. Anybody see sort of any difference between these two loading matrices?
These values are a little bit smaller.
Yeah, it looks a little bit cleaner, right? And again, if we go down through and we take a look, okay, so our pattern matrix is probably what we're going to interpret most times. Our structure matrix, this is going to give us the correlations between each one of our items and our outcome. And so the raw correlation here, so we see that each one of these items is sort of got a reasonably large correlation with the factor, right? Mm-hmm. But if we look at our pattern matrix and we're looking at unique relations, sort of item 1, strong unique correlation with 3. Item 2, strong unique correlation with factor 3, right? And so again, probably the pattern matrix, what we're looking at, our structure matrix, just giving the raw correlations. But then if we go down through, we look at our factor correlation matrix here. What are we seeing in terms of our factor correlation matrix, Trent?
These 3 different factors are correlated with each other.
Yeah, I mean, there's moderate correlations, moderate to strong correlations between each one of these factors. Family is related to friends at 0.46, to a significant other 0.59, significant other and friends 0.52, right? So we've got, so this is probably a reasonable solution here, right? It doesn't matter. I mean, everything, it doesn't change our interpretation of the factor. The factor is very clean. Items load very strongly, but we get a little bit cleaner pattern with the oblique rotation, and it probably sort of maps on better to our construct. So this would probably be maybe our preferred solution. But again, in terms of the proportion of variability or covariance in the solution that's being accounted for, your rotation strategy has nothing to do with that. Okay. Questions about this? So we say this is a beautiful measure, right? And maybe we say that this nearly perfectly maps onto our underlying construct. What might be your small reservation about sort of this measure? Any thoughts? You're going through and looking at individual items. What's that?
It overlaps too much.
Maybe. What do you mean by it overlaps too much?
Well, like for example, if your special person is your spouse, and it says family tries to help me, and then special person tries to help me, kind of measuring the same.
Okay, so some correlations between the two dimensions, right? What might be even more sort of concerning, if we're taking a very critical evaluation of this in terms of item wording?
They're worded very similar.
Yeah, right. I mean, probably what's going on. If we're thinking about good measure construction, what we want to do is we want to say, all right, what's my construct? And get a broad range. Like, we want to make sure that we're tapping into sort of all various components. Now, it's a trade-off, because as soon as we broaden out and so we start to be concerned about content validity of our measure, right? So if this is our construct, we want to make sure that we're assessing all components of our construct. Our factor loading, our solution is going to start to get a little bit weaker, because we're getting some things that are sort of less related, right? If we want to get a very, very narrow operationalization of our construct and basically ask the same question over and over and over again, we're going to get a very tight factor solution, but we might start to miss out on important, our measure might not capture important aspects of our construct that we're interested in looking at. Also here, there's some, this measure to some degree is capitalizing on sort of the phrasing of this, right? It's my friend, my friend, my friend, my friend, my family, my family. I mean, there are sort of aspects about this that are causing this to be a sort of extraordinarily clean thing. And so probably some of this is capitalizing on sort of the way the questions are written and tapping into that. And so wanting to make sure, always remember that sort of what you're seeing on the page and what this score, that's not a perfect representation of the construct. Probably we're getting sort of, and this is a good measure, use it all the time, so probably a good measure to the extent to which people believe they're getting support from friends, family, and significant other, but probably some of the cleanness is capitalizing on the fact that these items are all written with the same cadence, the same word, the same terminology, that's sort of heightening that solution a bit. So questions with this one? All right, let's transition over and look at something that's less clean, but not completely gross, like the last example. Your second handout here is an evaluation of some PTSD checklist data that we collected in the context of one of our lab studies. So these are people who have come in, who we've screened and have criterion A trauma, and we gave them sort of a popular checklist looking at severity of post-traumatic stress disorder symptoms. Okay, we've got 20 items here, and for those of you not familiar with PTSD as a construct, so the idea is that we have four distinct or four separate components of PTSD. Okay, we have intrusion symptoms. This is going to be things like nightmares and flashback, acute emotional physiological reactions. This is going to be items 1 to 5. Items 6 and 7 are targeting avoidance of reminders of this event. Items 8 to 14 are intended to capture sort of cognitive emotional changes, sort of difficulty feeling positive emotions, feeling detached from other people, blame, guilt, some negative affect and cognitive stuff there. And then 15 through 20, looking at increased arousal stuff. So we've got irritability, externalizing risk-taking, hypervigilance, startle, difficulty sleeping, difficulty concentrating, right? And so what we want to do is say, okay, so we should expect to get a 4-factor structure to this if these separate components are their own thing, right? And so what we want to do is go through and take a look and see, do we get sort of this same solution that we would expect based on the DSM-5 criterion. So, and people have your handouts, okay? We just pull up that second page of that handout. Going through, taking a look, what are we seeing in terms of our descriptive statistics?
A couple items are not normally distributed.
Yeah, and a couple of them are really not normally distributed, right? And so if we go through and take a look, right, if we flag PCL3, this is flashbacks, right? And again, this is a non-clinical sample. We would expect probably some skew in terms of this and some kurtosis. We're seeing sort of our numbing, sort of affective flattening has some skew in kurtosis. Anger also has some skew, more kurtosis, and sort of this risky behaviors, right? I'm engaging in sort of stuff that's dangerous to myself or others. That's considerably skewed and considerably kurtotic, right? And so it's something that we would want to know because it tells us something about our sample and how people are responding to these items. Now again, from a technical standpoint, not problematic for the purposes of our analyses, given that these are distribution-free procedures, but again, our solution probably isn't optimized here because we do have some deviations from normality, okay? So first thing that we're going to go through is probably going to want to run through initial principal components. And so again, I'll just do this just for time's sake, taking a look at on the page here. So our KMO, Sean, what do we think about a KMO? Are these items suitable for factor analysis? Yeah, why is that?
Because it's about
Yeah, these are 9. So these are sort of clear intercorrelations among these variables, right? So we get our initial commonalities. Looking at these, sort of more of a mixed bag in the MSPSS, right? We're seeing some really strong commonalities. It looks like extraction of eigenvalues greater than 1 are doing a good job of accounting for PCL12, PCL13, right? So we've got some high ones, but then we've also got some low commonalities here, right? PCL16 our solution isn't doing a great job with that. That's sort of taking too many risks or doing harm to yourself. So we're not, it's more of a mixed bag than in the last example. If we go down through and take a look at our eigenvalues, how many components did we extract from this, Lucy?
3.
3, right? So we extracted 3 components with eigenvalues greater than 1, and this is accounting for about 57% of the variability in our items. Okay.
But what about the fourth one's 0.988?
What's that?
Since the fourth one is 0.988.
It's not 1. Right? And again, this is sort of one of the questions back, it's right there, right? But if we go down through and we take a look at the scree plot, this is much more ambiguous than with the last one, right? Like if I look at scree, I'm like, 2, 3 maybe. By the time we get to 4, that's kind of a straight line, right? And so it's difficult to tell, right? We're accounting for, so when we go from, if we look at incremental variance, the first component accounting for over 40% of the variability in our items. Component 2 is getting 8%, 3 is 6%, but then I don't know what incremental of the next one is, right? So I'm having some problems knowing sort of exactly what I should be looking at in terms of reasonable solution. So what's the other procedure that we had talked about in terms of a way to go through and start teasing some of this stuff apart? Incremental variance. What else did we talk about? Parallel analyses, okay? If you look at your next page, and again, I gave you a handout talking about how you might go through and do that. I'm going to show you quickly what that might look like for these data. So what I'm going to do is I'm going to go through, and if this is my data or my syntax for this. So I've gone through, ran my principal components analyses here, but then what I want to do is I want to say, well, I want to run a parallel analyses. Okay, I've got my scree plot. What I want to do is go through and generate a number of random data sets to go through and plot the average eigenvalues. I'll run 10 of these, right? And what I want to do is I want to plot the average of 10 PCA solutions for the eigenvalues of drawn from random data and plot that against what I've got here to see, so what's the max number of factors that I should be looking to extract. And so what I've got here is, and I'm going to go through, shut that down. I'm going to go through, make sure always save this data as something else, because we're just going to turn it into random variables here in a moment. Or the computer's going to freeze up like a jerk. That's cool too. You joking, you think? Okay. Dice.
They freeze a lot in this room. Like,
Well, my SPSS like literally crashes every time I.
This whole IT is trash on this university. Like, it's ridiculous. It makes me furious. Essentially what we're going to do here, go through, and we're going to go through for each one of these items. You can see PCL 1 to PCL 20. What we're going to do is we're going to resave this data as something else, so don't screw it up. And what we're going to do is we're going to create a random variable between 0 to 4, right, the same scale that we have for our PCL 5, for each one of these items, right? So basically what we're going to do is we're going to generate a set of random data. And then what we're going to do is we're going to say, all right, what we want to do is we want to run a factor analysis, a principal components analysis with this random data that we collected. So what I would do in this case is throw this whole thing through the door. Go through, and this is easy to do. We can go through and highlight all that stuff in your syntax and just hit run, right? And then go to your table in SPSS, double click that, copy all your eigenvalues, throw it in an Excel, and do that just 10 times. Working across and what we're going to do is we're just going to run a total of, and I usually will do 10 PCAs with our random data. Okay. So this is what that might look like. So I've got items 1 to, or so eigenvalues 1 to 20. I've got 20 items, and so it's going to give me 20 eigenvalues. I'm going to run the PCA in SPSS, and then I'm just going to double click on that table, highlight my eigenvalues 1 to 20, and then paste them into here for random set 1. And then I'm just going to go to my, because the whole thing is highlighted in my syntax, right? Sort of all the variable, sort of the random variable codes, and then that final PCA, and just keep running that. And each time, I'm going to take the eigenvalues, drop them in here, drop them in here, drop them in here, until I'm going to run through 10 sets. And then I'm just going to take the average of those eigenvalues, paste them in here, and plot them against the eigenvalues that I got from that initial principal components. Yeah?
So on the syntax, when it says RV.uniform 0 to 4, it automatically gives a value.
Yep, it just random it. And so this is why you want to save your data first, because what it's going to do is for PCL, for all people in your set, for PCL 1 to 20, it's going to just impute a random variable between 0 and 4.
So it's going to change the existing value.
And it's going to change the existing value,
Okay.
right? But if you've got that all highlighted in your data, in your syntax file, all you need to do is just hit that, and every time you hit it, it's going to recompute a new random variable for all of your observations, and then run a PCL on each one of those. If you find you have the same eigenvalues each time you paste them in there, it means you haven't re-randomized your data each time, right? But if we do that, what we've got is average eigenvalues from completely random data using a set of the same size with the same number of people with sort of the same 0 to 1 parameter, and we're plotting that against our eigenvalues that we had extracted in our initial principal components. And so if you take a look at your handout, you'll see that that's listed here. And so what do we think? How many components should we be looking to extract from this solution? What do you think, Sean?
From the parallel analysis.
2, right? And so maybe 3. I mean, if I went through, I don't know, maybe I'll probably explore. 1 is certainly an under extraction. 1, 2, or 2, 3, maybe go through and see what's going on with that, right? And so you can see here in the handout, And again, so I know for a fact, just because I do this type of research, that we would expect that these factors to correlate, right? So what I'm going to do is I'm going to go run principal axis factoring, specifying a 2-factor solution with the Promax rotation to allow these factors to correlate, okay? And so if we go through, we see syntax side of that handout. Again, this is the percentage of covariance attributable to the factor, or the percentage of covariance in these items that's attributable to this 2-factor solution, right? And so again, looking down our commonality estimates here, not too bad, right? But it looks like for PCL3, this is flashbacks. We're only accounting for a little over 25% of the covariance. For PCL8, this is memory. We're only accounting for about 14%. PCL16, less than 25%. This is sort of risky behaviors. So we've got items in there that we're not accounting for a lot of the variability in those items, right? If we go down through, we took a look at our total variance explained table. Looks like our 2-factor solution is accounting for 45, a little over 45% of the variability, or the covariability in our data. So that might be a little low. If we go down through, we take a look at our pattern matrix, and looking at things that are sort of demonstrating strong loadings on one factor and weak loadings on the other, we see that on factor 2, we've got sort of unique loadings for item 1, 2, 3, 4, 5, 6, 7. It looks like we've got a cross loading on PCL2, right? So we've got a loading of 0.223, 0.387. It's pretty weak, right? So maybe we wouldn't pay too much of an example there. So PCL8 is also looking not great, as is PCL11. Looks like we have a cross loading there. But on factor 1, it looks like 9, 10, 12, 13, 14, 15, 16, 17, and 18. Looks like that's back on factor 2, and 19 and 20 back on factor 1. Okay. So our 2-factor solution here, we're not doing a good job of finding. We should be complex loadings for PCL8, which is memory, right? I don't remember important parts of the trauma. And PCL11, which is sort of just general negative affect. We see sort of moderate loadings on both of those, which sort of kind of makes some sense. And PCL2 is flashbacks. We're not sort of doing too good there. But in general, if we go through, and this is also wanting to go through and take a look at your marker variables, which one of those items is sort of has the strongest loading with your factor? And when you're going through and trying to think about sort of how to make a strong interpretation of your factor, so factor 1, highest loading by a considerable amount, is PCL13, okay? This is feeling cut off, feeling distant or cut off from other people. Highest loading for factor 2, acute physiological stuff, right? So these are kind of like the best indicators of what the core features of these factors. I would go through, based on sort of my experience with this, say it looks like we've got kind of a negative affect factor, sort of things like, so I'm feeling down or sort of guilty and sort of feeling bad about myself. I'm feeling depressed, not interested in things. I can't sleep, I can't concentrate. So just general negative affectivity, and then something that probably looks more like PTSD specific stuff on factor 2. So intrusive memories, nightmares, acute emotional responses, acute physical responses to stuff, hypervigilance, startle, is kind of how I would go through and maybe explain these two, okay? If I go through and I take a look at my factor correlation matrix, factors 1 and 2 correlated quite strongly, 0.66, but not to the point of being redundant, right? And so I might say, well, we're not accounting for everything, but I can't be in charge and start throwing out PTSD symptoms because I don't have the authority to do that. What I can say is this PCL, at least with this solution, looks like it's separating some generalized negative affect, some maybe more trauma-specific stuff, but we're not doing a good job of accounting. We're clearly defining memory, negative affect, or nightmares within the context of this solution, right? But also looked like maybe we could justify a 3-factor solution, right? It was right there under that cutoff, but we don't want to make sort of yes/no decisions. It's worth taking a look at. So if we go down through, we extracted three factors. Going down, so some improvement of the commonalities. Why does this make sense, Trent? Why would we see higher commonalities with the three-factor solution relative to the two?
More things that can.
Yeah, exactly. I mean, we've just got another factor in the model to account for stuff, so we're going to pick up some stuff. So we see incremental improvement in our commonalities. If we look at total variance explained, we've gone from, what do we have? About 45% of the variability down to up to about 50. If we look, that third factor is accounting for an additional just under 4% of the variability, which isn't a lot, but it's sort of not trivial, right? So maybe we are thinking that a three-factor solution might be a good way to go. If you look on the last page, look at the pattern matrix here. And again, we're looking for unique loadings. What I will typically do, and this is just sort of based on Comrie and Lee's stuff, what I try and do is say, all right, I'm going to call a salient loading something that loads at least 0.45 on a factor, so at least good, and less than 0.32 on other factors, right? So, and again, if I'm saying a good loading on sort of the target factor and sort of less than below what would be standards for a poor loading on other stuff, to be something that I would say, okay, it's pretty clean loading, right? And so here, so factor 1 now, we're getting PCL 12, 13, 14, 16, 19, loading on factor 1. This is going to be things like sort of loss of interest, feeling distant, cut off, having trouble experiencing different types of feelings, some concentration difficulties. Interestingly, risk taking is on here, which doesn't seem to make a lot of sense. It's not real consistent with the factor. So we got flattened affect, detachment, anhedonia, concentration difficulties, all which kind of seem sort of negative affecty to me. But then we've got increased risk taking, which is kind of a weird thing, right? So I'm having a hard time sort of coming up with what's unifying sort of all of these factors together. What's that?
I have an idea.
What's that?
Maybe it's like detachment. Because like maybe you're more apt to take risks. I know that this is not like this.
To feel alive.
Yeah, but like
Maybe, okay.
I'm trying to be
Right
more
on.
like more present. Like if I do this, maybe I'll feel something.
Okay, right. So and sort of self-harm types of thing might
Yeah,
play
yeah.
into that. Okay, so good, right? So thinking about sort of maybe that's what we've got with factor 1. Factor 2, this looks like more sort of trauma-specific stuff. Basically, this is the same factor that we got previously, re-experiencing stuff, avoidance stuff, hypervigilance and startle types of things. And then in 3, maybe some of these more cognitive symptoms like PCL 8 is going to be sort of negative beliefs about myself, other people, the world. 9 is going to be self-blame types of things. 10 and 11 is going to be flattened affect, loss of interest, loss of interest, detachment types of things. Is that right? Or no, blame, guilt, shame types of things. So more sort of cognitive-oriented types of sort of ruminative types of processes here. So again, it looks like we're not doing a good job of, or avoidance of thoughts and feelings. So that's going to be PCL 6, doesn't load cleanly on either of these. Our regression item, PCL 15, doesn't have a clear, strong loading on any of these. Same thing with sleep difficulties, sort of split between 1 and 2, right? And so if we go down, take a look at our correlation matrix, again, strong, consistent loadings across all of these, but sort of clear correlations between these. And so the task here with this is to say which one of these is a better solution, right? We clearly don't have evidence for, at least based on these data, for a 4-factor as implied by DSM, right? Based on these, that would be a clear over-extraction. I mean, we can do it, right? But the data is saying that you're probably capitalizing on just random stuff going on. Now, between the 2 and the 3, I don't know, right? I might say that the 2-factor solution is parsimonious. It's very clear. We've got sort of this generalized sort of negative crusty stuff that we would expect to go on. with many other things, and then we've got trauma-specific stuff. That's a nice, easy way to sort of break things apart. I'm going to stick with parsimony, and I'm going to go with this. Or you could make the argument, it looks like the 3-factor, it accounts for an additional 3% of the variability, 3 to 4% of the variability. I'm saying that I've got a decent sort of conceptualization of maybe what the underlying construct is that's driving these things. And so I'm going to put my money on a 3-factor solution, right? This is completely conceptual. There's no objective way to say this is right and this is wrong, okay? And this is where it starts to become important that you know sort of what you're doing, why you're doing it, what some of these analyses mean, and how you can go through and start teasing things apart, okay? Questions on this? All right. I've got you, also gave you that 60-page handout that we won't go through here, but this is a good example of what happens in real life when you try to make your own scale and what a nightmare that is, okay? With this is a sort of a stigma measure, sort of looking at different beliefs about trauma and how sort of symptoms develop and things. And so taking a strong conceptual theory and trying to write items that map onto different things, but when we sort of put them in the hopper and run them through, what actually comes out is oftentimes very different than what we get, right, or than what we would expect. And so we go down through, we get a general sense, right, and we say, okay, maybe it looks like this is a 5-factor solution, but we've got 7 different items that aren't doing much of anything. It looks like those aren't good, right? And so we get rid of those items, right? But as soon as we change an item, as soon as we change the items in the solution, it changes everything else. And so what we then might do is we run it again, and now we get other items and said things kind of fall in that 5-factor, but now it looks like maybe a 6 might be better, because things are sort of, every time we go through, do something, it changes things around, right? And so it can seem like an endless task of going through and playing around. So what if we keep this? What if we keep that? Other thing we want to be very careful and be mindful of is that these analyses are always going to capitalize on sample-specific characteristics to some extent, right? And so wanting to, if we run a factor an EFA in one sample and get something that we think is pretty good, it's probably worth running a whole nother sample to see if we get something that's at least in the ballpark of what we had gotten. If we get consistent pattern or consistent solutions within reason across these 2 samples, then maybe go through and collect a third and then run a CFA on that, a confirmatory analysis to see if this happens. And then what can be terribly frustrating is even if you've got a wonderful clean EFA solution across these 2, you're on the CFA, and the CFA looks like trash because it's a much more constrained model. You're basically saying, oh no, these items aren't correlated 0.1 with off factors, they're correlated 0, right? Which is a much more restrictive model. And so even if you have something that looks wonderful in EFA, Matt's disclosure scale that we've been collecting data on that, right? So there's beautiful 2-factor EFA. You run into CFA, and it looks terrible, right? And it's just because basically you're saying that anything that's not loading on this factor is loading 0 with other factors, which is an incredibly stringent criterion to test things against, right? And so wanting to walk into these analyses with clear eyes, they're messy, messy, messy. That MSPSS example was about your best case scenario, but I think there's aspects of that scale that have kind of a thumb on the scale that make it look sort of probably better. And so a lot of this is sort of going through and trying to find a solution that gives you a good theoretical conceptualization of what's going on, right? Item 12 may not load great, but from a conceptual standpoint, item 12 kind of needs to be on there because it captures an important component of this construct that I want to make sure is not left out. So I'm going to leave sort of that item in there, even though it's maybe not performing as well as some of the other ones. I could get a better solution with extracting that other factor, but it actually makes for a less parsimonious and more complex interpretation. So I'm going to stick with this, even though it seems like there could be a statistical improvement with this, but in terms of what I practically get in terms of theory, application, stuff like that is not worth it. And so not everything is about getting the lowest p-value or extracting the maximum amount of covariability in your data. So hope this was helpful. Go through, take a look, and again, have that other example walking through how ugly these analyses get and frustrating to the point you're like, don't even want to create my own scale. That's a dumb idea to start with. But if you have questions, I don't know, I like doing this type of stuff, and so if you come up with questions or have data or stuff you want to bounce off me, I'm happy to do that. So, cool. All right, folks.